So to mark the auspicious beginning of this program, we will now proceed with the ceremonial lighting of the lamp. I kindly invite our dignitaries to step forward and do the honors. To set the stage for this course, I now invite Professor Venkatesh Gurupadu sir to provide us with an overview of the Gian course. Let us welcome him with a warm round of applause.
Respected Director, Professor Vidyadhar Subudhi, respected Deans, respected Head of the Department Mechanical Engineering, today's distinguished foreign expert for current Gian program, Professor Pankaj Konikar from the University of Tokushima, Japan, and respected esteemed international resource person, Professor Kim from the Department of Ocean Advanced Materials Convergence Engineering, National Korean Maritime and Ocean University. Respected senior professors, my dear colleagues, students and participants, a warm welcome to you all and a very good morning. On behalf of Mechanical Engineering Department, it's my privilege to present an overview of today's Gian program, which is focused on advanced low-dimensional nanomaterials for green energy, optoelectronic, and healthcare applications. Nanomaterials have grabbed significant attention due to their unique properties and immense potential for applications across various sectors, particularly in the development of efficient and sustainable energy solutions. Materials like graphene, metal oxides, and nanocomposites are also showing great promise for energy storage devices like batteries and supercapacitors. Nanomaterials can be functionalized to deliver drugs and great specificity and controlled release, improving healing outcomes which minimizes the side effects. Nanomaterial-based biosensors also hold the potential to transform disease diagnosis and monitoring by enabling rapid and sensitive detection of biomolecules. This course provides a comprehensive overview of all these nanomaterials, which exhibit remarkable characteristics at the nanoscale. The sessions also explore ongoing research in energy harvesting, energy storage, and electronic transportation, with a special emphasis on efficient optoelectronic devices and conversion appliances. Additionally, this course covers the synthesis and manufacturing techniques for reducing material size and fabricating nano devices. The course offers a balanced perspective on both the physics and engineering aspects of these materials, with a brief overview of the latest research in nanostructured materials for sustainable applications. Lectures are planned along with the tutorials and interactive sessions, giving participants an opportunity to gain hands-on experience and unlock the full potential of these materials for various applications. We are pleased to see a great response to this program, with participants hailing from international, from the University of Chile, and also hailing from various corners of the country, such as VIT Vellore campus, NIT Andhra Pradesh, NIT Tiruchirappalli, and also several well-known private institutions. Throughout this course, participants will have the privilege of learning from eminent experts and resource persons from esteemed institutions, including University of Tokushima, Japan, and National Korean Maritime and Ocean University, South Korea, and our very own NIT Warangal. So these distinguished experts will share their invaluable insights into the latest advancements in nanomaterials and their applications. Once again, I extend a warm welcome to all participants, and I am confident that this course will be a highly enriching experience for each one of you. Thank you very much.
Thank you, sir. Now I invite Professor Ravikumar Sir, Head of Department of Mechanical Engineering, to give us an insight into the achievements and vision of the department.
Respected Dean RNC, Professor Sirish, Professor Pankaj, the international expert for this Gian course from University of Toshima, Japan, and Professor Kim, the other expert from National Korea Maritime and Ocean University, South Korea, the coordinators, Dr. Venkatesh and Professor Vamshi, senior colleagues, and my dear colleagues and students, and the very importantly the participants, a warm morning to you. So this is the third Gian course from Mechanical Engineering Department we are conducting under this phase 4 of Gian series of courses. And coming to the Department of Mechanical Engineering, so Department of Mechanical Engineering exists right from the inception of the institute, that is from 1959. Department presently offering one undergraduate program in BTech in Mechanical Engineering with an intake of 165 and 5 MTech programs in various specializations like thermal engineering, manufacturing engineering, computer integrated manufacturing, machine design, and automobile engineering. So department is also offering doctoral degree in various fields of mechanical engineering. Presently, department has 90 full-time and 40 part-time scholars on rolls. At present, department has 50 regular faculty with a research expertise in various mechanical engineering areas. And we have good academic labs, which is equipped with experimental facility like 6-axis milling machine, IR camera, CNC lathe machine, computerized fuel cell test rig, 3D printing, additive manufacturing machines, friction and wear tester, air jet erosion, wheel alignment, vehicle onboard diagnostics, to name a few. And the department has also licensed with reputed industries and R&D organizations such as NFTDC, DMRL, DRDL, RCI, ASL, ARCI, BHEL, GTRE, ADA, and so on. The department has acquired a funding about 5.5 crores under externally funded projects from DST, SCRB, DRDO, DMRL, etc. The department also has Center for Sustainable Energy Studies and Hexagon Capacity Center as Center of Excellence. And also Department of Mechanical Engineering is associated with Center of Excellence for Digital Manufacturing and Automation. So with a few note, so I request this program a grand success, and I want to appreciate the efforts made by the coordinators, the two coordinators, for making this Gian program a grand success. Thank you.
Thank you, sir. Now it is my privilege to invite Professor Gangadhar Adu, sir, to introduce our esteemed chief guest, Professor Pankaj Konikar, sir.
Good morning to you all. So it's my pleasure to introduce Professor Pankaj Koinkar. So he began his research career as a junior research fellow in the Department of Physics in 1999. He earned his PhD in physics, that is in material science, in 2005 from North Maharashtra University, India. After completing his PhD, he joined the Department of Physics at the University of Pune as a research associate from April to September 2005. He then moved to Korea University in Seoul, South Korea, where he pursued postdoctoral studies from October 2005 to September 2006. Following his year in South Korea, Dr. Koinkar joined the Center for International Research and Educational Cooperation at Tokushima University, Japan in March 2007 as an assistant professor. He became associate professor in March 2016 in the Department of Optical Science at Tokushima University. Additionally, since April 2021, he has served as the Vice Director of the Center for International Cooperation in Research and Educational Cooperation at the same university. Dr. Koinkar's research areas include 2D nanostructures, laser ablation in liquids, photocatalysis, field emission microscopy, sensors, and engineering education. He has published over 122 papers in peer-reviewed international journals and has received 2 awards for his presentations at international conferences. Thank you.
Thank you, sir. Now I request Professor, our today's chief guest, Professor Pankaj Konikar, sir, to deliver the inaugural address. Let us give him a big round of applause.
Good morning to Professor Kim from Korea, Professor Shri Sonone from NIT Warangal, Professor Ravi Kumar and Professor Venkatesh, Professor Vamshi, Senior Professor and my dear friend and participant. This is one of the occasion where one has to talk for 1 week. Such kind of program is good for the student. Actually, 1.5 years before, when I was interacted with Professor Venkatesh, we were thinking what kind of program we should conduct so that it will be unique and good for the student. So since I am working on the nanomaterial, various kind of nanomaterial, and that nanomaterial can be the part of this program, so I started to think about the program, maybe topics, and I come up with the idea that we can have a topic on the nanomaterial. Nanomaterial, how nanomaterials are important, how we can synthesize those nanomaterial, and what kind of application, especially in the field of energy, because we will face some energy crisis in the future. To address this energy crisis, we have to find out the sustainable solution, and nanoparticle are the prime candidate for finding some kind of maybe solution to the problem of regular or daily use energy. So energy is one of the application that nanomaterial can fulfill, and beside that, not only in the field of energy, but healthcare is also one of the application where nanoparticles, nanomaterial can be widely used. So This course is about nanomaterial. I will conduct the basic of nanomaterial. Then I will also teach how we can synthesize those nanomaterial. And beside this, there are various applications in the field of energy, optoelectronic, and healthcare. So I will cover all those topics. But those students who are not well aware about the nanomaterial, they will learn many things about nanomaterial. Because when we talk about the nanomaterial, this nano means very small particles. And if you compare that nanomaterial, let's consider your human hair. So if you take your one hair and compare that hair with the nanoparticle, so 40,000 nanoparticle can be sit or accommodate on single hair. Nanoparticle we cannot see, but we can imagine how small these material. Although the particles are small, but their application is very big. So those kind of application is very useful. And in everyday life, we are using the product. Those products are based on nanomaterial. So these products are very few, but in future, we want to have more application based on the nanomaterial. So those application will be created in future. But from now, as a researcher, we have to work on those topics. So with this course, I want to motivate the student so that they can enhance their research in the field of nanomaterial and nanotechnology. So I would like to thank the organizer, especially Professor Venkatesh, Professor Vamshi, and Department of Mechanical Engineering, as well as faculty provided by the NIT Warangal, so that this course is conducted smoothly. Thank you to all of them. Thank you very much.
Thank you, sir. Now I invite Professor Manjeha, sir, to introduce our international resource person, Professor Kim, sir.
Good morning, one and all. Good morning to the dignitaries on the dais and as well as off the dais. It's my pleasure and honor to introduce our one of the Gian, the foreign resource person for this 1 week workshop, Professor Kim. He was born in Daegu City in Korea and received his BS and MS from the Materials Engineering from Korean Maritime and Ocean University in 1983 and as well as 1987. He also received master degree from the Mechanical Engineering University of Tokushima in 1990. And he has received his PhD degree in Mechanical Engineering from Kushoko University, Fukuoka in 1993. And Professor Kim was a visiting professor in National Institute of Standards and Technology in 1997 and at Naval Postgraduate School in 2019 in USA. And he is currently a professor at Division of Maritime Equipments Engineering at Korea Maritime University in Busan. And he also a vice president of the Korean Society of Engineering Education and the editor-in-chief of Nanohybrids and Composites and also the Advanced Engineering Forums. And he was a director of the Innovation Center for Engineering and Education at National Korean Maritime and Ocean University. And he founded the Asian Conference Engineering Education in 2009. He trying to promote innovation engineering education through the cooperations with Asian countries. His research areas includes the composite fabrication, evaluation of its strength, physics metallurgy, and is the author for the 5 books, and he has published more than 300 papers in the reputed international journals, and including his essay index of the 140 essay papers in the reputed international journals. He has also received an awards from the domestic and as well as from the international for the oral presentations in the journal papers during the conferences. Now he is president for the Korean Society of Composite Materials. He delivered the plenary speech in 2024 at ACCM 13 conference Kyoto in Japan. He is a current Gian expert and as well as the honorary the professor in the Kim University and Korea. He is developing astroloid nanotubes to improve the mechanical properties in the current research areas. Thank you very much for giving us the opportunity to deliver his talk in this Gian workshop. Sir. Thank you. Sir.
Very good morning, everyone. I am from South Korea, from Busan, located in southeastern tip of Korean Peninsula. Our university is established firstly as a national university in Korea. Yeah, so this is it is a great honor to be here and to make a speech. Welcome to the inauguration of a highly anticipated Gian on advanced low-dimensional nanomaterials for green energy and optoelectronic and healthcare application. So as the president of the Korean Society for Composite Materials, it is immense pleasure that I witness the convergence of bright minds and pioneering spirits in the realm of nanomaterials for green energy and optoelectronic and healthcare application. Throughout this 5-day conference, we are honored to present an array of enlightening sessions. This diverse spectrum of knowledge and expertise promises an enriching exchange of ideas and discoveries that will push the frontiers of science and innovation. Nanomaterials represent the pinnacle of scientific innovation with the potential to revolutionize industries, fortify sustainability, and transform our technological landscape. The intricate world of nanomaterials has unveiled groundbreaking applications across diverse sectors, from healthcare and electronics to aerospace and sustainable infrastructure. In closing my talk, I urge all of you to seize the wealth of opportunities presented by this conference. Once again, a warm welcome to Gian. May the conference be a wellspring of inspiration and enlightenment for all in attendance. Thank you for your presence and contribution. Thank you so much. Have a nice day.
Thank you, sir. Now I request Professor Sirish Sir in R&D to share his thoughts and insight with us.
Good morning. Professor Kim, Professor Pankaj, coordinators, senior professors, head of department, and my dear colleagues and the participants. Actually, it's very great honor to see Professor Kim is here in NIT Warangal. This is the 8th visit of Professor Kim in India. And Professor Kim is very well known in the composite area. So all the PhD students are requested to take maximum we have been try to be interact with Professor Kim. Because this networking is very important for the research is concerned. I mean, we got an opportunity to be visit at our during doctoral time abroad, and we remain connected with them. So the Professor Kim also have been. I mean, Professor Koinkar was initially visited Korea, then both have been connected. Like they are in the Japan and Korea collaborations is there. So like Professor Kale from the CMET also, Professor Kim is coming and they have been connected. So this networking is very important. So I request all the PhD scholars try to interact with him and can it find out the possibility to work with them. Maybe a small conference you can visit with them, and I'm quite sure both of them will agree to arrange that one also. So I also request Professor Kim, our mechanical engineering department and chemical and other material science we have department definitely will have the visits also. So we can think that how we can make this composite material area, we can take it ahead. Maybe Korean Society and NIT Warangal, can you have some collaboration also? As a president, you can help us. So thank you very much for inviting me. Thank you.
So, very good morning, sir. Very good morning. Yeah.
Thank you, sir. Now it is my honor to invite our director of NIT Warangal, Professor Vidyadhar Subudhi, sir, to deliver the speech online.
Thank you so much, sir, for your kind wishes. Sir, please occupy the.
Now I request Venugopal sir to come on dais. I request the chief guest, Professor Pankaj Konikar sir, to open the course material. Now I request Professor Ravi Kumar sir to give memento to Professor Pankaj Konikar sir. I request Venugopal sir to give memento to Professor Kim sir. Thank you, sir. To conclude this inaugural session, I invite Professor Vamsi Krishna sir to deliver the vote of thanks. Please welcome him.
A very good morning to all the dignitaries on the dais and off the dais. It's a great honor to me to propose the vote of thanks on this occasion. I'd like to specially thank international expert Professor Pankaj Koyankar, who accepted our proposal and came all the way to share his knowledge with us. I am indeed delighted to have Professor Kim from South Korea, and we thank him for his presence and sparing his valuable time. I thank our director, Professor Vidyadhar Sabudhi, for his constant support to conduct such an activities. I wish to record our sincere appreciation to Professor S. Srinivas Rao, a local Gian coordinator, for encouraging us to conduct this program. I thank Professor Sirish Sonaven sir, Dean R&D, for his presence to this inauguration session. I'd like to thank Professor Y. Ravi Kumar, HOD, Department of Mechanical Engineering, for his support in organizing this course. I especially thank my friendly colleagues Gangadhardu and Manjaya to help us in this inauguration program. I also thank Professor Venugopal sir for sparing his valuable time on this occasion. And I thank all the mechanical department staff, supporting staff and students And I extend my thanks to campus office and all the supporting staff for their assistance and managing the facilities here. I also thank distinguished invitees present here. I thank and at the last, I thank all the participants here, and I ensure that your 5 day stay at our campus will be fruitful, and you can learn something new from this course. And thank you, one and all.
Thank you, sir. Now I request everyone to please rise for the national anthem. Yeah. Thank you, everyone. Kindly now I request everyone to have a group photo session followed by high tea at the designated area.
So dear participants, so you can take snacks and tea, and the session starts at 10:30. Okay? So 10:30 to 1 today. ఇంకెవరన్నా బయట ఉన్నారా? లేదా? So once again, good morning. So we are going to start our first session on introduction to nanomaterials. So we have our first session expert, Gian expert, Professor Pankaj Konikar from Tokushima University, Japan. So I would like to invite Professor Pankaj sir to take over the session.
Okay, thank you, Professor Venkatesh. So this course will start today. Just we have opening ceremony, and from now I will have about seven talk related to the nanomaterials, its synthesis, application. So the first talk is about introduction to the nanomaterial. Before understanding its properties, application, we must understand what is nano means. Once you understand the real meaning of nanomaterial, nanoscience, nanotechnology, it is easy to understand its property as well as application. So let's start the journey with the introduction of nanomaterial. When I am going to teach you, if you have any question, you can stop me in between and you can directly ask the question. I will be answer your question. Or at the end of the talk, you can ask the question. Either way is okay for me. So, introduction of nanomaterial will cover what is the real meaning of nano, how we can imagine the nano means, what is nanoscience means, what is nanotechnology, and what is the new and different about the nano, why nanomaterials are special, what is the different property they exhibit from the bulk material, and why they are special material. That we are going to see in the lecture 1. As you know, 50 years before, the airplane was small, but demand of people traveling from one place to another place increases. So when demand is increases and you have small space, so what you can do, you increase the space. For example, if in this room only 200 people can sit, however, if the participants are more than 200, what you will do, you will increase the space. You have to build the new rooms to accommodate that people. Similarly, when there was small plane, number of people can accommodate was 100, then maybe 200, and these days we can carry 400 people also. So what does it shows? It shows that things might be big when we require, when demand is there. So this demand comes out with the bigger idea, bigger space. So we increase the size, small plane to bigger plane. Now in this case, what happened when people want to use the airplane in larger quantity, the size of the plane is become bigger. So this way, this problem was solved by making a bigger plane. So sometime size is important. Size is important. Now, when we consider the size, it might means small size become bigger size. So big size might be bigger and bigger may be better depending on the application. So sometimes size can become bigger from small size to big size. So bigger size can work in many ways. But sometimes if you want small thing, very small thing, then you have to think in reverse direction. Take a bigger things, make a small things, and make it useful. So that concept of making big things into small things is nothing but considering the thought of small material. So those small materials are nanomaterial, because bulk material has bigger size. But when you go to the deeper scale, to the smaller scale, to the nano scale level, the thought, the idea of nanoparticle come out that can we make the big particle into small particle? If our answer is yes, then that answer is nothing but a nanomaterial. So some cases bigger size better. In some cases when we think about the smaller size, smaller particle, and those particles are nothing but nanoparticle. Now the concept of size is very important. So you might born after 2000, but if you know the history of smartphone, earlier smartphone was very bigger in size. You cannot handle easily. We called it as a mobile phone, but the size was bigger. So if you look at this way, how this big smartphone changes into small smartphone. Why this happened? Because we are using the same phone now, but the size is changing. What happened? Why we are using the small size? Because the material that has been used here, they are in small size. If you don't understand, take another example of television. 30 years ago, television or computer PCs are very big, and now PCs are very small. Why? Because the component used in the earlier television, smartphone, they were big, and now the component is in micron size, so that we can see the small size of smartphone or television. So in this case, we come with the bigger and ends into the smaller size. So both way we work. This is big to small. Okay, we started with the big things and ends up with the small things. When you make anything which is small, it is happen because of the component, because of the change in the size. So now the revolution in mobile phone, smartphone is a good example of understanding the size, because size is very important. But when you think about any kind of materials, nanoparticles, those materials are made up of or available in the solid, liquid, or maybe gases or plasma state. When we talk about the solid, they have continuous arrangement of atoms. So that is solid. In case of liquid, they are loosely bound. So some of the atoms are bound together, but some of the atoms are loose. That's why it is in liquid state. And in gaseous state, they are free particles. They cannot connect to each other. That's why they need bigger space also. And in case of plasma, it is a charged particle. So there are 4 states of matter. So when we talk about any material, the material is available either in solid, liquid, gases, or plasma state. So this is the basic of material or state of matter. Now, how these atoms are arranged? So atoms may be arranged two ways. If you consider any kind of material, there are two ways you can find the arrangement of atom. One way is uniform. Now you can look at, you can see the atoms are uniformly arranged, okay? One rows, another. It's a similar kind of arrangement. But if you look at this way, okay, here it is arranged, but here there are something gray and so two type of atoms. So this is kind of defect. So when you have any material whose atomic arrangement is this way, so it will behave differently. If it is arranged this way, it will behave differently. What is means behave? They will exhibit a different property. So if they exhibit different property, then we can use for a particular application. So we have to deal with this, because when we talk about the nanomaterial, nano means it is almost on the atomic scale, 10 to the power minus 9. So it's all about the atomic arrangement. If you don't understand last slide, let's look at this slide. So what this slide suggests to you, you take any cloth, t-shirt, shirts. You use it for 2 years, 3 years, 4 years, 5 years. Somebody might use more year. But it will tear. It will have some kind of hole. Why this happen? Because the bound, the atom which are bound together, the fiber which are bound together, they become loose and we can see those kind of holes. Now we cannot use this cloth. So the thought how we can make the cloth which can intact longer. So if you want to intact the t-shirt or any cloth as it is for several years, again it will come to the atomic scale. So you need to control their atoms so that they cannot easily break. Is it possible? Can we control the atom? So controlling atom is a new thought. If you control the atom molecular structure, then there will be totally new field in the field of nanomaterial, nanotechnology will come out. But in future, if we control these individual atoms, if you control this individual atom, then we can get the solutions of many problems. But practically, can we control the atom? That is the question. If we want to control the atoms, then we have to deal with the quantum mechanics. So quantum mechanics is very hard subject to understand. If your major is physics, you might be understand easily. But I will explain you in simple way. If you want to control the atom, we need a certain kind of environment where this atom cannot move easily when we are making them together, at least when we are making those kind of material. So their bond become intact. So how we can make it? At certain temperature, at certain pressure, if we make this atom very strong and they can connect to each other, then in future we might get a different kind of material. So these days researchers are working on nanomaterials and they are thinking about controlling the atom. So in future molecular structure may be possible. So why I am telling you this story? This story is about nano. When you talk about the atom, so atom is 10 to the power minus 10 and nano is 10 to the power minus 9. So that's why such kind of materials is nothing but a nanomaterial. Nano is available in nature. You have seen by your eyes, but you have not realized. Some of the example of the nano is, have you seen the butterfly? So butterfly change its color, wings color. When they expand their wing, you can see change in the color. Have you seen the peacock? So peacock also change the color when it expand its wing, okay, like this. So you can see the rainbow kind of color. So what is that? That is nothing but nano. So that is available in nature. Other example, have you seen the lotus leaves? Water cannot stuck. So that is hydrophobic property of leaves. So those are some example you can see in the nature, and those example give us inspiration to make the nanoparticle. So nature already making the nanoparticle, and with this inspiration, nanoparticle can be made in the laboratories. So now, to understand why we are making this nanoparticle, what is the reason, what is the objective, what is the main purpose, why researchers are actively working in the field of nano? Because this nanoparticle has application in our day-to-day life. So solar cell, have you seen the solar cell? Solar cell is good example of nanomaterial. In solar cell, silicon metal is used, or silicon thin film is used to make the solar cell. These days research is going on. Can we replace this silicon, amorphous silicon thin film by perovskite material? So here they use nanoparticle and they make the electricity. To create the electricity using the sun, and source is sun, material is solar cell made up of nanoparticle. This is one of the example we use in day-to-day life. And another example is, can we use the nanoparticle for cancer treatment? Yes, we can use it. I will explain you this in detail when my talk about the application in health center, healthcare will cover this topic, how nanoparticle can be used in healthcare. There are various applications, not only cancer. Besides cancer, there are many applications. I will cover few of them. So it is possible that they have optoelectronic application, they have healthcare medical application, and other application is sustainable application, such as contaminated water can be converted into the clean water. So that is using the again solar light. So that we call as a photocatalysis, and I'm working on photocatalysis. So I will also explain this part when I will conduct the lecture, application of nanomaterial in the field of green energy. So I will cover this topic there. So these three examples suggest that nanomaterials have application in various fields. It is not limited to chemistry, physics, biology. It can be used in various fields. So various field means there are basic subjects like physics, chemistry, biology, but if you combine this physics, chemistry, biology with material science, engineering, technology, everywhere nanomaterial will be found for certain application. So in future, nanoparticles, nanotechnology will be very important branch to make them useful in various applications. Now nanoparticle, can you see by your eyes? Actually you cannot see by your eyes, but you can observe by your eyes. When you rub your pencil, what you are doing? You are creating nanoparticle. So nanoparticle means this is graphite. Okay, graphite is the bulk material. But this carbon atom, the graphite is made up of carbon atom. So when carbon atoms are attached to each other, and mechanically when you rub the pencil, you are giving some kind of force, mechanical force to the pencil, so that pencil is rubbed on the paper, and what you will find, there are small graphitic particle. So if you see this particle are nothing but carbon particle, because bond between carbon and carbon atom is easily break when you apply mechanical force or pressure. So this way you can create nanoparticle. However, we cannot actually see them. If you want to see this nanoparticle, you have to use TEM or SEM. So in future, nanoparticle is a powerful technology. If we use the nanoparticle, then those nanoparticle can be utilized for various applications. But how to use this nanoparticle for a good application, that is the main objective, main challenges of the researcher. So now, if you want to think about the application, so application do not hurt to the common man, to the society, to the environment. So application should be sustainable. If you are doing the research in the field of nano, try to consider the application which is not harmful to the humankind or not harmful to the environment. It should be sustainable application. Then and then it can be used practically. So always think about sustainable application. It cannot be harm to society or humans. This one slide can give you the idea how nano is small as compared to the bigger things. So these are 1, 2, 3, 4, 5, 6, 7, 8 pictures. So I will explain, I will show you rather than explain. This is 1 meter scale. So in 1 meter scale, there are flowers, there are leaves, rose flower and leaves. So if you consider only one leaves now, this is 1 meter, okay? So this is 10 centimeter. So 10 centimeter means we are talking about this length, okay? This is 10 centimeter length. So if you reduce or zoom it for another 10 times, now 1 centimeter. You can see the fly clearly. So now this is 1 centimeter. So 1 centimeter means our thumb, roughly from here. So on your thumb, this fly can sit or stay or accommodate. So 1 centimeter, now 10 times, 0.1 centimeter. So when we say 0.1 means 100 micrometer. 1 centimeter, we can see this head. But if you go 10 times below the scale, you can see the head of the fly. That is 100 micrometer. That is 0.1 centimeter. Then again 10 times, we zoom it. Now we can see the clear spikes. Also we can see here in 10 micrometer. Then goes to the 1 micrometer. Now you can see this spike clearly. That is 1 micrometer. Still nanometer is not. Now 1 micrometer, this spike, okay, has 100 nanometer. 100 nanometer. Now this is on the 100 nanometer scale. We started with the leaves and flower, but we end with that spike between on the head of the fly. And those spikes is made up of some kind of DNA. Those DNA has some kind of protein and their arrangement is like this. So this is 10 nanometer. But this structure is made up of atom. And atom is in 1 nanometer there are several atoms, maybe 6, 7 depending on the atom size. So 1 nanometer, sometime oxygen has 8 atom can accommodate in 1 nanometer. So this way you can imagine the scale. If you want to understand the scale size in the larger scale, in the opening ceremony I give you one example that human hair, depending on our diameter of the human hair, if it is 50 micrometer or 100 micrometer, so you can imagine this human hair is 50,000 or 100,000 nanometer in wide, diameter, okay? So that many nanoparticle can stay. If you take this one hair, so 50,000 or 100,000 nanoparticle, which is made up having the size of 1 nanometer, can accommodate on this area, 50,000 to 100,000 nanoparticle. And there are other example like a simple small pinhole, okay, small pin we use to connect something or make the hole. That is 1 million nanometer, 1 million particle can sit on that diameter of pinhole. So this way you can imagine, or simple example, any paper, the thickness of this paper is 75,000 nanometer. So on this paper, simple paper, and look at the thickness, 75,000 nanoparticle can accommodate there. So hopefully you can understand the concept of size, because understanding nanomaterial, first of all you must know how these nanoparticles behave when they go to the nanoscale, and how about their size. When you want to imagine the nanoparticle, you must imagine this way, because some application are in very small scale. So you must know in one hair how many nanoparticle will there. If collectively when you are talking about 100,000 nanoparticle, 1 million nanoparticle, what will be the area? On that area these nanoparticle can stay on. So 1 nano is 1 nanometer, or 1 nano is 1 billionth part. Like 10 to the minus 9 meter. 1 nanometer is 10 to the power minus 9. That is nanoscale. And in earlier slide, I have shown you various examples and compare their size. So these nanoparticles can be found, or in the laboratory we can make these nanoparticles with various shape and size. For example, nanosphere, nanorods, nanosheet, nanocage, nanocube, nanostar. So this particle we can make in the laboratory. Why different size? Different size and different shape is the key parameter for the nanomaterial, because different size and shape decide the property, and once their property is decided, they can be used for a certain application. So I will show you the next slide, that is various kind of nanomaterial, various size and shape. Nanolayers. So when we talk about nanomaterial, what is the size of the material? Usually 1 nanometer to 100 nanometer. It may be in layers. So most of the nanoparticle can be found in nanolayers. So nanolayers or nanotube, nanocube. So nanotube, again with the same specification. So nanotube is one of the type of nanomaterial, and this nanotube, how this nanotube can be created? Diamond, graphene, or you can say this fluorine or carbon nanotubes. So tubes can be made. This is graphite. This is graphite. So it has a carbon ring there, and this is the bind. Okay, they are attached to each other. If this length is broke, and this sheet is separated, then graphene is created. If this sheet is wrapped, then another type of material is created. So those material we can create in the laboratory. Other type is nanoparticle, simple spherical particle, nanoparticle. So these are nanoparticle with different shape, usually circular or spherical, and different shape like star, cube, sphere, plate or rod can be created. And last one is quantum dot. The nanoparticle can be found in quantum dot. So 2 nanometer to 10 nanometer. If the size is 2 to 10 nanometer, it's called as a quantum dots. Now why we need this particle, and how about their size? Because if you change the size, okay, let's say this is 100 nanometer and this is 20 nanometer. If you consider this particle, this is a kind of nanomaterial, and when you put light on it, they exhibit a different color. That is their luminescence property. Because nanocrystal size determined by their gap, and they exhibit a certain color because of their band gap, You can see as we change the color, their band gap also changes, and once band gap is changes, you can find the change in the color. That was about nanoparticle. Then nanoscience means what? Nanoscience is the science of making the things from the small material, small stuff, small particle, nanoparticle. So any study which deals with the small particle, tiny particle, nanoparticle is nothing but nanoscience. So nanoscience, it's not biology, physics, chemistry. It can be used for various fields. So this study of or science of small material is called as a nanoscience. So nanoscience is the study which include the phenomena and manipulation of material at atomic, molecular or micromolecular scale. When we talk about the nano, it should be in the nanoscale, 10 to the power minus 9. So the materials which is called as nanomaterial, and if you are studying those material, that field is called as a nanoscience. Now here basic scientists like physics, chemistry, they are working on certain property. So basically what they are doing, they are studying nanoscience. Then this nanomaterial can be used in various fields. Practically, this application is available in our daily life. Sunscreen, cosmetic, stain resistant clothing, electronic, tires and medicine. Various kind of nanoparticle, nanomaterial is used. Zinc oxide, TiO2, carbon or iron oxide or carbon black powder used for a particular application. This application is already exist in our daily life. We are using it. If you want to see this, maybe when you are buying sunscreen, you can see the component. You will find a certain kind of oxide material is there because they can block UV light. So that is their property. That's why it can be used for sunscreen. If you don't block UV light, then we cannot use it. So do you think that a bulk TiO2 powder can be used for sunscreen? No, because it cannot block UV light. If bulk TiO2 can block the UV light, then we will never use nanoparticle. So that's the beauty of the nanomaterial. At nanoscale, they exhibit different property. For example, bismuth selenide is an insulator material when we consider it as a bulk material. Totally insulator, we call topological insulator. But when it goes to the nanoscale, it behaves like semiconductor. So that is one of the things, how these nanoparticles behave, how they exhibit different property. It may be because their band gap changes, it may be because of their size, shape. So those property can be used in particular application. Now, I have shown you various examples. Let's have one challenge for you, but don't Google it, okay? Don't Google it. If you have a smartphone, do not use smartphone for time being. A human fingernail grows particular nanometer in every 1 second. You look at your fingernail, it grows, okay? You just look at its growth. It is in nanoscale. Every second it is growing. Or man beard or our hair. It grows every second. You touch it, it's grown. Now, anybody has any idea about this? How much fingernail meter? Okay, so nanometer I already explained you. Anyone can have idea that our fingernail, you cut your fingernail maybe once in a week. So have you measured how many maybe in length you cut your fingernail? Anyone? 1 nanometer. Wow. 1 nanometer, 1 second. How about either beard or mustache or hair? Any other idea? Okay. So 1 nanometer. Now it is average, okay? Somebody's might be 2, 1.5, somebody's maybe 0.8. This is average. So now, next task to you. This is 1 week course. If you are nail today, you check how much it grows in 5 days and try to measure its length. You will find your answer. About the man's beard, it grows about 5 nanometer. So, cutting your nails and cutting your hair 5 times, okay? 5 times. But we cut our nail fastly because we cannot grow it longer. Our hair can grow longer and then we cut it. We feel that nail grows like slowly, but it grows fastly than the hair. So this is nanotechnology in your body. Outside, okay, outside. Some of the example I have given which is already available in the nature. Lotus leaf, okay, or butterfly, okay, or peacock. Those are natural example of nanotechnology, nanomaterial. And this is, nature has given us nanotechnology in our body outside. And inside also, inside, if something is cut, our skin heal immediately. That is also kind of nanotechnology. Nanotechnology. Have you imagined that? How our skin can join together. Even we wound our maybe some kind of cell that make it possible. To understand how small we create nanoparticle in laboratory. This is silver nanowires which has diameter, let's say 500 nanometer. So you took one silver nanowire and tried to put it on 60 micrometer here, 60 micrometer. There will be 120 nanometer silver nano wires can be put on this here. If this is 50, then that number will be 1000. If it is 5, then that number will increase. So this way, it is possible to decrease the size and see how small we make the nanoparticle. Nanoparticle, ideally it should be 1 nanometer to 100 nanometer. Then what is nanotechnology? What is nanotechnology means? We have seen nano, we have seen nanoscience. Then what is nanotechnology? Nanotechnology is the art of making any device, instrument which consists of nanoparticles. So when you are making any kind of device, instrument, equipment which consists of, made up of nanoparticle is called as a nanotechnology. So those nanoparticles might have different size and shape within the less than 1 micron. Ideally it should be 1 nanometer to 100 nanometer, but in some cases like maybe nanotube, their length is in micron. So if you are dealing with any device, any structure, any system, any equipment which having the particle below 1 micron is nothing but nanotechnology. So nanotechnology term is discovered by Japanese professor Taniguchi. So he was working in the field of microscopy. In 1980, he is the first person who invented this term, nanotechnology. Technology term was available, but he joined this nano and technology, make it this word nanotechnology. So it was in 1980s, 40 years ago. Actually, research in nano was initiated in 1990s from carbon nanotube. But what is the special things? Why these nanomaterial are special? What is the reason? This is the last part of first talk. Why they are special? What is the different thing nanomaterial has? Using nanoscale material, something which is made up of nanomaterial, or understanding nanomaterial. These are two different things. Using nanomaterial means you just use the nanomaterial for certain applications, certain maybe device. That is one part. Another, you understand them, you study them deeply. These are two different things. These are two different things. When you want to do the research, you might deals with, you use the nanoparticle, or your study include, you understand the nanoparticle. Now what should be your aim? Your aim is to understand the nanoparticle rather than to make the nanoparticle. If you understand the nanoparticle, how this nanoparticle exhibit optical, mechanical, magnetic property, what is the reason, that should be your motive. That's give you inspiration to work more. So try to understand the nanoparticle if you are making the nanoparticle. See their property, how these property are different from nanoparticle, from bulk particle. Understand them. What is the reason? Try to find out the reason. So that deep study is very important. So you can learn two things. Either you can use the nanoparticle, either you can understand the nanoparticle. So for those practical purposes, research is going on. But if you want to see the nanoparticle, you need some kind of machine or tool that is on nanoscale. So transmission electron microscope is a good way to understand the shape, size of nanoparticle. And there are other technique also. This is visually you can see their images. but there are other technique like UV visible, XRD. There you can predict that these material are in nanoscale. So, what is the different thing? Why nanoparticles are special? They are special for two reasons, especially two reasons. There are other reasons, but two reasons are more. One is their size. Size is very important. So, if you have size, small size, that size decide the property, and that property is the key element for that nanoparticle. So size is one of the factors that govern the property of nanoparticle, and another is reactivity. Now what reactivity means, what size means? So size, if you understand the size, let's consider this gold bar. Okay, so everyone has something gold in their body, or they have seen. So it is in yellow color. When you make the nanoparticle, gold nanoparticle, you can see color is changed. Why this happen? This happen because when gold, bulk gold, transform into nano size, it exhibit a different kind of optical absorption. It can absorb a certain color, and that color is nothing but their property. This is not possible in bulk. If you cut a small, this is big, okay? You cut only small part, put into the water and see the color. Color will not change. That is practically impossible. Otherwise, you can put the water on gold and you can see the color. So for bulk, it is not possible. But nano, it is possible. So this is the optical property of a nanoparticle that changes the color. That changes the color. So this is the effect of size. This is the effect of size. So yellow become a different color. Now this yellow color can be converted into different color. It is possible because of the size. Another example, this not only color, sometimes they can be exhibit, or you can add some more tool like UV light or some other light and try to play with them. They can be used for different kind of property, or they might exhibit different property. Like melting point of nanomaterial is lower than the bulk. So gold has certain melting point. But nanoparticle, it is in small and its melting point is lower. Now this is another chemical property. Optical property, color is shown. Chemical property is this. So that's why you change the size, two property change, and this property can be useful for certain applications. Shape, okay? Now you can not only size, shape, rods, shell, or nano case. Look at the, so change in color can be seen. So this change in color is nothing but their optical absorption. So here, if it is a rod, you can find blue, red, but if it is nanoshell, you can find green also. Green is not possible. Here yellow is possible, here yellow is not. So size and shape can affect the property of nanomaterial. And another is reactivity. So what is reactivity means? Reactivity means how the atoms are arranged within the nanoparticle, and how this outer shell of nanoparticle, they react with the certain medium. It may be air, it may be liquid, it may be another particle. That reactivity is different when we consider certain nanoparticle. Whether they are arranged like this or they are arranged like this, it will all depend. If they are arranged like this, size will be bigger. If size is small, then again their reactivity will be different. So how much surface how much surface is available for reaction. So if you consider bigger, only this part, and this part is available. 1, 2, 3, 4, 5, and down 6. 6 part is available for reaction. But if you break them into small part, okay? So now this part, this part, this part, this part, down and back. 6. Then 6, 6, 6, 6. So the area will be more for reactivity. So that's why if you consider bulk material, small area is available. If you consider small material, nanomaterial, big area is available. So that is the another property that decide whether these nanoparticles are good or not. So surface is important. This is one more slide. Now here it is a cube of sugar, okay, and this one separate sugar cube, okay. This is a big cube. Big cube is made up of small, okay. Size is bigger here. Although they are bind, okay, they are attached to each other, and this is they are separated. You put them into the liquid. Now, which one will dissolve fast? Which one will dissolve fast? Anyone? B. If you understand the earlier slide, answer is correct, B. When you make the particle very small, the reactivity is fast, okay? Because the reaction can take place from all directions. So this case, you try this example. You take the bigger sugar particle and you take the smaller, you put them into the liquid and try to stir them simultaneously. You will find this will dissolve fast. So this way, nanoparticles react, and that's why they are special. They are special. And this, why they are special? It is because of their size. It is because of their size also and surface area available. So when I show you the bigger cube maybe let's consider on larger scale 4 centimeter. So surface is this much available, okay. But when you make small, okay, so this much, and then how many cube will be accommodated here? So smaller, they always have larger area for reaction. So there are two important factors that decide the property of nanomaterial. And in my next talk, I will tell you about the sizes, shape, and different kind of methods to prepare the nanomaterials. And after that, we will move to the application. So today, first talk, I will stop here and we can have some short break. After short break, we can continue the next talk. Maybe after 5 minutes, we will gather here. 7 minutes, we will gather here and we can move to the next part. So let's have a break. But before that, if you have any question on today's talk, please ask question. Please feel free to ask the question. Any question about introduction? Yes, please. How we can? So when I told you that when you are considering the application should be sustainable to the society, to the human being. What kind of material you are using? For example, if your application is for medical purposes, so we cannot use a random particle. Like I told you, silver particle may be good for antibacterial activity, and that can be possible use in human body. That cannot have any side effect on. But if you think, oh, zinc oxide I will use for medical, no. Our body will not accept foreign particle. It will have certain side effect. to reduce the harmful effect for particular application, first of all, you consider what kind of material will be good. Whether you are thinking medical application, electronic application, or any type of mechanical or any type of application, you start with the material, whether this material is good or not. This is first thing. Yes? That was like ZNO TiO2 I show for sun outer. This skin has a certain kind of thick screen. It cannot, goes into the screen. But I'm talking like if you use some material, okay, and you use for sunscreen, but it has side effect. When it react with the light, skin might burn, might be black. That is side effect, because light has certain energy, it will react. So that is one example. That is outside. Inside also, inside body for medical. If you use certain material, that might not be good for the application. So which type of material you use for a particular application? Are you doing certain research? What kind of material? Nickel cobalt. For okay. So if you are using nickel cobalt, see that what will be the byproduct. Whether if you use this material, it will create some kind of byproduct which is harmful to the environment. That you have to think. Another thing, whether these material will be easily available, whether these material are rare. So those all things you need to consider, and then maybe it will reduce the effect, harmful effect on human being or maybe on the environment. So some material are good, some material are poisonous or might have some side effect. Those parameter you need to consider. Any other question? Please ask question. Question is important. Without question, we cannot improve ourselves. Okay, so it is 11:32. We can have a short break of 6-7 minutes, and we can gather here 11:40 if there is no question. Of course, you can ask me question during the break also. Okay, so let's stop here. Okay, we will gather 11:40. Thank you. Okay, let's start the second talk about types of nanomaterial. This is the second topic that we are going to learn. Today morning you heard about me, and I want to know about you. So can we have a short introduction about you? You can tell your name. You can tell also what kind of student you are, master, doctoral student. And also, if you are doing research, you can briefly tell about your research, that I am doing research in this field, so and so technique I am using, and so application. So within 1 minute or 30 seconds, you can wind up your introduction. So we can have the small introduction from the participant. So can we start from here? You participate.
machining purpose. Yeah, yes. So that's the area where I'm just focusing on. Thank you.
So my name is Soli Matthew. I'm a doctoral student at VIT Vellu. Working on capacitive pressure sensor for e-skin application and basically working on or exploring the nanocomposites for the same applications.
I see, I see. Okay, thank you very much.
Thank you, sir.
Hello, sir.
Yeah.
My name is Suyash Wagurde. I'm currently doing my master's from North Maharashtra University, Jalgaon, and currently engaged in the project work on the organic light emitting diodes, fabrication and characterization on that.
Okay, thank you.
Good morning, sir.
Yeah.
My name is Mukund Dekunde, and I'm from Dr. Bhavsa Ambedkar Marathwada University from Aurangabad, and I'm doing my master's in nanotechnology, and I'm currently working on transitional metal oxides for energy storage applications.
Okay, thank you. Next one.
Sir, my name is Desika. I'm a PhD scholar of VIT University, and my work is related to production of vanillin. It is an aromatic compound using bioprocess technologies.
Okay, thank you.
Good morning, sir. This is Niveta. I'm also a PhD scholar from VIT Vellu. So, my work is like fermentation technology. I'm currently exploring nanotechnologies for that purpose.
Okay, thank you.
Sir, good morning, sir. Myself, Rama Prabha. I'm a PhD research scholar, VIT University, Vellu, sir. So my research area is nanotechnology, and I'm using photocatalyst. Zeta nanobit I'm using, sir.
Okay, thank you.
Good morning, sir. I'm Lakshmi Priya. I'm working as a research scholar in VIT University. I'm working in tissue engineering and regenerative medicine based on bioprinting and scaffolds.
Okay, thank you.
Thank you. Good morning, sir. Myself, Karpagalli, working under environmental remediation towards with the help of sludge treatment of pharmaceutical with the help of titanium catalyst.
Okay, thank you. Hello, sir. Yes. Use mic. We have. Thank you.
Hello, sir.
Yeah.
Myself, Dr. Vikas Yadav. In my PhD, I have worked on microchannels, heat enhancement through microchannels for cooling purpose. So I am now trying to use nanofluid inside that microchannels.
Okay, I see.
I am from Pune. Right now, I am working in Nutan Maharashtra College of Engineering, Pune.
Nutan
Maharashtra Institute. Yeah.
Okay, I see. Okay,
thank you.
Good morning, sir. Myself, Dr. Digvijay Patil.
Yeah.
I'm working in same college.
Okay.
And research area is related to composite material.
Okay, I see. Thank you.
Sir, good morning, sir. This is Shrikant, sir.
Yes.
I am working as assistant professor in Rayalaseema University, Kurnool, Andhra Pradesh, sir.
Okay.
Now I am in the research scholar under the guidance of Venkatesh, sir.
Okay.
My research topic is microwave processing of polymer matrix composites, sir.
Okay.
Thanks.
Thank you. Okay. Any other participants? Yeah, please. Is okay? Yes. Okay. Thank you. So I just want to know what is your background. Of course, most of you are working or eager to work on the nanomaterial. So nanomaterial is the core material for most of you. And second topic for this course is types of nanomaterial. In earlier, I told you that there are two important factors that govern the property. Of course, there are several other parameters that can also control the property of nanomaterial. So, nanomaterial can be divided into several type of material, and that material we call classification of nanomaterial. So first talk was just the introduction, and I can see most of you are working on nanomaterial. So how much you understand the nanomaterial? Which one of the following material cannot be seen by a simple microscope? Please listen the question carefully. Which one of the following material cannot be seen by a simple microscope? Okay, I got two answers. One answer is correct. Simple microscope. Okay, simple microscope. Which material cannot be seen? Cannot be seen. Okay, so bulk material means you take this one, okay, and put in the simple optical microscope. You will see something. You will see something, because optical microscope can gives you the information up to micron level. Okay, I'm talking about simple microscope that has lens up to 200x or 300x. But you cannot see nano material, okay, nano material. That's why the size is more small. You have to use the other equipment such as scanning electron microscope or transmission electron microscope if you want to visualize the nanoparticle. So this was the tricky question, okay. Which one of the following is the example of nanomaterial? Nanosilica, sand, cement, all of above. Nanosilica. Anyone has a different answer? Nanomaterial, nano. Now sand, you go to the beach and you see the sand. Those are not, some particle may be nano if you see the dust on that, and if you are considering that will be, but what you can see, they are in maybe few micron or even millimeter. So sand is not nano, no way. Cement particle not in nano actually, if you, because those particles we can see by our eyes, okay. By the way, our eyes can see any particle up to 2.2 millimeter, that is 200 micrometer. If there are two particles, this is one particle and this is another particle, and if you put them together, okay, and both particle size is 200 micrometer, you put them together, okay, like this. Now this is one particle, this is one particle, and try to see by your eyes. You will see those two particles separately, okay. That is, our eyes has the, you know, maybe level, or you can say ability of our eyes to see something separately. But if the size of this nanoparticle and this is 100 micrometer, you join together, now you will not able to see these two particles in a separate. What you will see like they are connected to each other. So that is our eyes, you know, resolution, we cannot go beyond that. Up to 0.2 millimeter we can see the things clearly. So in cement there may be mix, not really nanoparticle, they might be microparticle, because our eyes can see. If they are nanoparticle, our eyes cannot see. Our eyes cannot see it. The gold bar and silver bar are the example of bulk. So this means you have seen lecture number 1 carefully. There I have shown you bulk gold, and this way you are understanding. So these bars are bulk, not nano. The color of nano gold particle is yellow, orange, red, or variable. Good. So this means now you are getting the things. Of course you already study, but it's interesting to cross check whether you are understanding it or not. So variable means gold nanoparticle can be seen in different color as per their size. Quantum dot can be used in up to, okay, quantum dots, very small particle, okay, 2 nanometer to 10 nanometer. These are the ideal size of quantum dot. So they are mostly used in optoelectronic, because opto is light, and quantum dot behave differently when they are in this size 2 nanometer to 10 nanometer. So those quantum dot, most of the quantum dot is used in optoelectronic for emitting a different kind of light due to their band gap. Okay, that was a quick quiz for you to make you live and review our earlier talk. Let's move to the types of nanomaterial. So type of nanomaterial is classified into 4 types: 0-dimensional nanomaterial, 1-dimensional, 2-dimensional, 3-dimensional nanoparticle. Now what is 1-dimensional, 2-dimensional, 3-dimensional material? There is 4 and 5-dimensional, but our research is limited up to 3-dimensional at this moment. So we will study one by one. What is 0 dimension? What is 0 dimension means? What is 1 dimension means? What is 2 dimension means? And what is 3 dimension means? So 0 dimension is the first type of nanomaterial. 1 dimension is another type of nanomaterial, and 2-dimensional material is the third, and 3-dimensional is the fourth material. Now here this green part, okay, this green part is considered as a 0 dimension. But you start with 1 point, okay, 1 dot. You put 1 dot. I don't know whether they have some pen here. Okay. So when you start with the 1 dot, green one, connect 1 dot with another dot, okay, 1 dot and another dot. This 1 dot and another dot is connected. So when you connect 2 dots, then it becomes 1 dimension. Okay, so you started with 1 single dot and you connect those 2 dots by certain length, certain things, or combine them, or join them, then it becomes 1 dimension. Like you are making the chain, okay? So how you make the chain? You make 1 circle, okay, and then you add another circle, then 3rd circle, and this chain increases. Similarly, 1 dot, another dot, 3rd dot, you connect 1 to 2, 2 to 3, and expand. That is 1 dimension. 2 dimension. So now you have this, single length or maybe up and down, but it is 1 length, whether it is in zigzag or straight line. 1 dot, 2 dot, 3 dot. So this is 1 line. When you connect this 1 line, for example, this line with this line, when you connect 1 line with another line by something, then it is 2 dimension. So in 2 dimension, you connect 1 line with another, and you have connected. So this becomes 2 dimension. When you connect 2 dimension 1 unit with another unit, it becomes 3 dimension. Now what is the example? What are the example of this 1 dimension, 0 dimension, 2 dimensional, 3 dimension that we are going to see? But why this nanoparticle is considered as a 0 dimension as a one dimension, as a two dimension. In case of zero dimension, they are dots. They are dots. In case of one dimension, they are in one line. Like you can have one rod, but it can grows in one direction only. One direction only. So this chain will increase either in this direction or either in this direction. It cannot grows in this direction, it cannot grows. Why? Because this zero dimension dot is a basic dot. It will not increase its size. It will not be bigger, okay? If it is a quantum dot, for example, 2 nanometer, so it will not increase its size. It will not grow in X, Y, and Z direction. It will be as it is, okay? And when that as it is particle you connect it, you make a chain. That is one dimension, okay? So chain line. And layer. The classic example of two-dimensional material is, let's consider any paper, okay? So if you have paper, that paper will increase in X direction and Y direction, X direction and Y. So paper can be extend, okay, horizontally or vertically. So like this is the paper, okay, or let's consider this is one paper, but it can increase in this direction and this direction. But we cannot increase the thickness. We cannot increase. If you increase the thickness, it will be no more paper, okay. So two-dimensional means it can extend, it can increase in two direction. That's why it is two-dimensional. So if you are playing with the nanomaterial and it extend in X direction and Y direction, two-dimensional. If it extend in X direction, Y direction and Z direction, then it is three-dimensional. Three-dimensional. Okay? So when another slide will come, you will understand how this nanoparticle is classified and why they are called as a zero dimension, one dimensional and two dimensional. So no, it's dot. It's, quantum dots, it's dot. Basically, it's single unit, okay? Because when you consider chain, okay, chain is one unit, but it is made up of small, rings or maybe simple small unit or small point you connect with each other, okay? So that make big chain. Although we called it as a chain, but they are bind with something, okay? Like, do you remember I told you about the pencil, okay? So when you rub the pencil, it is a graphite, three-dimensional, okay? But the sheet that is two-dimensional, carbon sheet and another carbon sheet is attached to each other and that makes three-dimensional. Graphite is a three-dimensional structure, but when you rub, what happens? This sheet and this sheet is connected, but this connection is broken and this sheet becomes separate, this sheet becomes separate. So this way you create the carbon particle or maybe graphene, okay? Because graphene is nothing but this sheet. If it is connected, it becomes graphite. So three-dimensional can convert into two-dimensional if the bond breaks. This way, one paper, XY direction, that is two-dimensional. And this third one, you can have two-dimension, one paper, you connect one paper with another paper. This is one paper. If you connect another with certain bond, then it becomes three-dimensional. Three-dimensional. Like you take your smartphone, it is three-dimensional. You take rubber, anything which has X, Y, and Z. If it has thickness, then it becomes three-dimensional. Here there is no Z direction. We are not considering thickness. Okay, we are not considering thickness. Here nothing, not thickness, not width, not nothing. Dot means dot, finish. So that's why it called as a zero. There is no way it can extend in any direction. That's why it is zero dimension. So let's move to the next slide. This way you will understand if you don't understand the first slide. The bulk material is bulk, okay? Bar of silver Ag. Anything which is in your hand and it has X, Y, Z axis, X, Y and Z. X, Y, this one is Y, okay, this is X, this is Y, and let's consider this is Z. So if it has, or there is a possibility that this bar will increase in 3 directions, 3D. If you cut this into the pieces this way, then it is 2-dimensional. Now what you are doing, basically you are cutting this axis, okay? Earlier we were considering this axis, but you are cutting this into the several pieces. Now here, this axis is become negligible. That's why it is 2. Now possibility that it will extend in this direction and this direction only. Because this direction you already, make it into pieces and vanish. And then next you cut this part from here, okay, and make it like rod, okay, rod. So this is 1 dimension. And this you again cut into small piece, then it is 0. So this way you understand we have big bulk particle that is 3 dimension. You cut into 1 direction, then 2D. You cut, again reduce 2 to 1, and from 1 you again cut it into 0 dimension. So this way you can see what the particle size, how they classify into a particular class like 3-dimensional, 2-dimensional, and 1-dimensional, 0-dimensional. So these are the way you should understand how nanoparticle is created when they make. I told you, you should understand nanoparticle. When you are making the nanoparticle, if your nanoparticle start with bulk material and convert into quantum dot, you should understand physics and chemistry, how this nanoparticle is created. Do not concentrate on the last part. You should concentrate how these things happen. That is the research. Making nanoparticle is also part of research. Understanding nanoparticle is the real research. So try to understand what physics, how reaction happen, how this wall is break, how this rod is created, how this quantum dots is created. That is the real research. So why this kind of different nanoparticle is required, whether it is 3-dimensional, 2-dimensional, 1-dimensional, 0-dimensional? Because they can be used for a particular application depending on their properties. So each bulk material also possible to use for several. We are using traditionally bulk material everywhere. So that is no way that we can going to reduce the bulk. Bulk material has application, like I show you the airplane. So we cannot deny that we are using the bulk material. That is there and we will use it forever. But bulk material convert to 2-dimensional, certain application. 1-dimension, certain. 0-dimension, certain application. So it will depend on their property, what kind of property they exhibit. To understand it in a simple way, like we have again smartphone. So sometime this smartphone, some smartphone give quick response, okay? So when you scroll down, it give quick response than other. Or maybe 2007, iPhone was launched for the first time. And the touch technology was invented, or it was maybe come into the market for the first time. So what happened actually when touch screen become bigger? Now you can see that this thing happened, but have you understand the physics behind it? Why this touch technology is improved, whether for smartphone or whether for notebook, mobile, desktop, any kind of PC or monitor. The performance is better. The touch screen is better. That is, by your eyes you can see. But how it has been improved? It has been improved by the material that sense. When you touch your finger, the sensitivity time is less. If the sensitivity time is less, then the touch performance or it can improve. So it is the material property. It is the material property that show you the performance. And we are always in the search of material that shows high performance. This is one of the example. There are several examples. Smart window, certain kind of material can be coated for something to reduce corrosion, to reduce the maybe blocking the UV. There are several examples. So one of the example is this: by reducing the particle size, improving their performance, either by reducing their size or adding something so that the property can be changed. Now I was telling you about the 0 dimension, 1 dimension. I believe that you understand the concept of 0 dimension, 1 dimension and 2 dimensional. So this 0 dimension means all dimension are in nanoscale. Remember, okay? 0 dimension means all, everywhere, x, y, z, it is in nano. It is in nano. 1 dimension, okay? In 1 dimension means actually 2 directions, okay? 2 directions are in nanoscale. That I will show you in next slide. Then 2 dimension, 1 dimension is nanoscale and 2 dimension is microscale. 3 dimension, that is most of the bulk material. Chances of expanding, increasing in 3 direction, you can make very big. No dimension, it has on nanoscale. Okay, remember, for 3D material, okay, these are 3D material, pencil, graphite, 3D material, okay, their length is in not nano. They might made up of nano, but their whole length is not in nanoscale. So we are going to see them, how these nanoparticles can be made in a certain dimension. So for time being, this is the density of state. It's a real physics about the 2 dimension, 0 dimension. Means what happened when we think about 3 dimension, 2 dimension, 1 dimension and 0 dimension, how this density of state affect the property. So density of state is a function that describes number of state available in a system and essential for determining the carrier concentration and energy distribution. If you remember, I was telling you about the reactivity. So if you want to understand the density concept, if you are not physicist, just remember that how many charge carrier is available for reaction. That way you can correlate this one. So number of carrier, that carrier means certain carrier is available in all material, and energy distribution of those carrier within material, within semiconductor is nothing but the density of state. So as per these kind of material, 2D, 3D, it changes. This is the example, okay? 0 dimension means it's almost circular. They are not connected, although I have shown you here, they are not connected. They are individual particles. And this is nanofiber, nanotube, these are rods. So it can extend in one direction, okay? This rod goes here, here, here. No problem. It may be 1, 200, 1 millimeter, no problem. The key point is this one, okay? This one axis, okay? The diameter will be in nanoscale. Length will not be in nanoscale. Diameter will be in nanoscale. Here, this and this will be in nano material, but nanoscale. Two-dimensional means thin film, coating, or sheets. These are two-dimensional. X and Y increase, okay? Two direction can be increased, Z direction cannot, because we are not concentrating on the thickness. This thickness will not change. This thickness will not change, but it can extend in this direction too. And 3D is like this. So X, Y, Z, and you can connect those blocks together, make big things. That is three-dimensional. So it is basically many crystal. Those can be connected to each other and it becomes three-dimensional. And these are the real example which has been taken from the research paper. So zero dimension, especially nanoparticle, okay, especially nanoparticle. One dimensional, it may be nanotube or nano wires like this, maybe hollow or filled with something. Two dimensional, basically sheet-like structures or these kind of nanoplates or nano belts. So either it has a special shape or maybe belt-like or sheet-like structure. So this will increase in two direction, and these are building blocks kind of structure, that is 3D structures. So zero dimension means which type of material. Zero dimension means it is a dot, it is a particle, and it cannot extend in any direction. There are various nanoparticle, nanomaterial, those called as zero-dimensional material can be prepared in the laboratory. They might be amorphous or crystalline. I hope that you understand the difference between amorphous and crystalline. Today, first talk, slide number 3 or 4, maybe 4 or 5. I shown you that atoms arrange in certain order, okay, and atoms arrange not in certain order, they might have defect. So randomly arrangement of the atom is amorphous, like powder, okay, they cannot bind together. And crystalline is a solid crystalline material, like sugar has certain shape, graphitic has structures. So if you measure their XRD, you will get strong peak. But if you measure the amorphous peak, it will not be a straight peak. It will like hump kind of structure. So this is the difference between amorphous and crystalline. So those particles might be amorphous or might be crystalline, but they are zero-dimensional. So it may be single, it may be polycrystalline. So individual particle might be found separately, or some particle might be connect to each other, okay, like this, might connect to each other. So their connection might be loose or they are just laying on each other. And it can be composed with single material or multi or nano composite. Maybe you can combine one element, another element, make a composite. It is possible that one quantum dot, another quantum dot, you can make heterojunction or combine or binary, or you can say composite material from two different kind of elements. Various shape and size is possible. So quantum dot also has shape and size from 2 nanometer to 10 nanometer. It exhibits individual or incorporated in a matrix. So you can make it separately, or you can put this zero-dimensional nanoparticle into separate nanomaterial. Those nanomaterial might be 3-dimensional, 2-dimensional, or 1-dimensional. You can use this zero-dimensional material for making nanocomposite material. And they might be metallic, ceramic, or polymeric. So there are many different elements. It may be metallic, zinc, AU, AG, tin, tungsten, or ceramic, any oxide material, or polymeric material. It is possible to create the quantum dot or zero dimensional material. So here you can understand this concept. They can be found in various shape and size. So nanomaterial is 1 to 100 nanometer, but quantum dot or zero dimensional material, they are the individual material. Usually their size is 1 to 10 nanometer when we talk about the quantum dot. But some nanoparticle has bigger size and they cannot extend. They cannot extend because what happen when they grow in the single unit, their single unit might be 20 nanometer, and after that they cannot increase. So ideally quantum dot is 2 to 10 nanometer, but in some cases some nanoparticle might have a bigger size. And this zero dimension can be found in different kind of shape also. So remember, they cannot extend in any direction. Okay, so both x, y, z direction will be limited for them. It cannot extend further, and their size will be always less than 100. So these are one of the example of these nanoparticle, which we call them as zero dimensional material. Zero dimensional material, and this zero dimensional material, they are single line or polycrystalline, or maybe they found in single unit or maybe multi-unit. They can be metallic, ceramic. Those kind of material might be amorphous or crystalline, and this is one of the example you can see on the nanotube. These nanoparticle can be grown. This is another zero dimension. So here they are single unit. They are single unit. Okay. Once they form, they cannot increase their shape. They cannot increase their shape. That's zero dimension. That they're zero. And AU is the classic example that can be shown to the student to understand if their shape, size change, how their optical property change. Then next one is one dimension. You connect one dot with another dot, it become one dimension. It become one dimension. What is the example? Any kind of nanotube, any kind of nanotube, like you are making chain, okay? You are expanding in one direction. Or a rope, you consider rope, okay? Or wire. So wire can be extended in one direction only. So that is one dimensional material. So those also has the same size. And example, wires, nanotube, nanorods are the example of one dimensional material. It can be amorphous crystalline. Here also same like a zero dimension. Single or polycrystalline is possible. Chemically pure and impure. Which technique you are using, depending on that, it may be pure or it may be impure. If you are using chemical reaction, sometime you might get some byproduct, impure. If you are using some kind of physical technique in the vacuum or in the liquid medium, you get totally pure material. So which technique you use for synthesis, that decide the quality of the material. And another, like you can use this material to make the nanocomposite. Again, metallic, ceramic, polymer, all type of material that can create the one-dimensional material. But most of the one-dimensional material are oxide material. So whenever you read or see the paper, most of the material is oxide or maybe individual metals. So this is the one dimension, okay? So only one will expand. Only one will expand, and these are the examples. Length will expand, but diameter will intact. Diameter will never change. Diameter will never change. So why this diameter is not going to change? Because when you want to extend the rods, the rope, the tube, this tube, rod or rope cannot extend in this direction. If you try to extend, the shape will collapse. The shape will collapse and the growth will be uneven. So that's why these kind of shapes are special shape, and we cannot extend, increase their diameter. If it is 100 nanometer, it will be 100 for all the cases. Even though this length is, let's say, 500 nanometer, it might be 1 micro, 2 micro, 10 micro, but diameter will remain as it is. That's the special property of one-dimensional material, one-dimensional material. So to understand this, you can consider carbon nanotube. So this carbon nanotube diameter remain as it is, even though they are double wall, multi-wall carbon nanotube. No matter how many layer inside that, 1, 2, 3, 4 rings, how many, doesn't matter. But overall this diameter intact, and this length can be changed. So here nanotube, nanofiber, nanowires, nanorods, examples of the one-dimensional material. This carbon nanotube was firstly invented by Professor Iijima in 1991. Carbon nanotube is very good material. However, its property was limited for certain application, and unfortunately it cannot grow that much as it is expected. After this carbon nanotube, graphene was first invented in 2005 and it got Nobel in 2010. So after 2010, everybody is doing the research in the field of graphene and they totally forgot carbon nanotube. Otherwise, after the invention of graphene, carbon nanotube is almost vanished. Very few people are doing the research for special application. So this is the examples of one-dimensional material. Nanotubes might be hollow or maybe filled with someone. So these are more example. Fibers. Earlier was tube, okay? This is tube and fiber. So tube, hollow, okay? This is all, nothing, empty. And fibers, like fibers, okay? These are the example, and they have certain maybe diameter. Length may be big, you can see this big, okay? So this is 10 micrometer, okay? This scale from here to here, it is 10 micrometer. I'm not sure you are seeing, but this is 10 micrometer. So if you consider, this may be 70, 80 micrometer. But look at the diameter, it is 0.5 micron, that is 250 nanometer. So diameter is not changing, length will increase. Like you have many ropes and they are entangled with each other or they are connected to each other, but their diameter is same. There are more example of one-dimensional material, nanowires, nanorods, nanotube, nanobelt, nanoribbon. So these are example. It can grows in one direction only, Next class of nanomaterial is two-dimensional nanomaterial. Two means two direction, X and Y. So those material can look like sheet or plate like structure. Plate has certain width and sheet don't have that much width. So it include nanofilm, nanolayers, nano coating. So nano film, you can deposit certain nanofilm of two-dimensional material, or nano layers, you can coat nano coating, certain thickness of material, you can just make or use the coating technology to coat a certain material. So it may be thin film, it may be coating, or it may be just a single layer. So two-dimensional, again, same as 0 and 1 dimension. It may be amorphous, it may be crystalline. Various chemical composition, you can make those material. Why various chemical composition? Because we use a different kind of bulk material or chemical, mix them together, and we might have various combinations. It can be grown in a single layer or multi-layer structure. So single layer means, imagine, single layer means it has only one layer, like sheet-like structure. So sheet-like structure, paper. And multi-layer structure means you can imagine one paper, another paper, number of paper on each other. So most of the two-dimensional structures are found in layer, one, another, like you are putting 10 paper on one paper, another paper, third paper, like this. So you are making the group of 10 paper, 20 paper. So they found in multi-layer structures. Of course, they are not attached to each other, but they are just laying on that. Okay, they are just laying. They are not connected to each other. They are loosely just, they are laying on top of one another. So those can be found in single layer. If you are using like physical technique, you can make single layer. But when you make the chemical technique, so in chemical process is continuous. After formation one layer, another layer also form, then third layer also form. And it can deposited on various substrate. It can integrated with matrix structure, means multi-structure, composite material. Again, metallic, ceramic, polymer structure is possible. So this is two-dimensional structures, and two-dimensional, as we learn that it will grow in two direction. It will grow in two direction. Okay, X and Y, X and Y. So any structure which is look like sheet or paper, it is two-dimensional structures. One dimension, it at nanoscale. That is only one dimension is at nanoscale. Other two will not be, because this X and this Y will extend. Okay, so that will be no more in the nanos. However, this part will be nano. The thickness of that sheet will be nano. Like this. This part will increase, this part will increase, but this will not increase. So this length, X direction, Y direction will increase, but Z direction will not increase. It will remain intact, and usually it will be equal to 100 or less than 100. Then and then it is two-dimensional material. So two-dimensional material is widely researched by the researcher all over the world because of their spatial property. So these days, most of the research paper is on two-dimensional material. Why? Earlier, one-dimensional material, mostly oxide material, already studied. And when the invention of graphene occurred in 2010, after that people started to work on various two-dimensional material, and they are getting better performance, better research. That's why two-dimensional material is more popular than one-dimensional and zero-dimensional. Of course, they can be useful to make the composite. Take a two-dimensional material, add one-dimensional material, zero-dimensional, make a ternary composite and improve the performance. Whether you are talking about the hydrogen production or photocatalysis or any type of maybe application, combination of this two-dimensional, one-dimensional, zero-dimension definitely improve the properties. So two-dimensional material are the special material, and those material can be used for a certain application. So these are some of the example. Let's consider this kind of example. It may be look like sheet or petal of flower, okay, petal of flower, or comb-like structures or platelet-like structures. So most of the structure is sheet. Most of the structure look like sheet, okay, or petal of flower. So those structures are nothing but two-dimensional structures. This is nanoplates. Plates has a certain thickness as compared to sheet. Little high thickness than the sheet material, but they are still the two-dimensional material. Then three-dimension bulk material. Most of the bulk material or X, Y, Z direction can be increased in three ways. Those materials are called as three-dimensional material. So three-dimensional materials are having the multiple arrangement. Why multiple? We started with one dot, that is 0. Then one dot connect another dot, one dimensional. One line connect another line, two dimensional. Then one sheet connect another, then it become one three-dimensional unit. And one three-dimensional connect another, make multi-component. Like one room, another room, second floor, third floor, it make a building blocks. So this way it grows. Like if you have one thing and you want to grow similar thing, then you make this one unit, another unit. So 0 dimension, one dot. If you want to increase, another dot will come. 3 dimension, one unit, another unit. And one unit is big, another bigger. And it will keep increasing. So it look like it is a multi-storage, multi-block structures on the nanoscale, So this three-dimensional material is difficult to make. But it has a certain kind of features or property like dispersion property, or bundle of nanowires can be considered in three-dimensional structure, nanotube or multi-nanolayers. I told you reactivity is very important. Reactivity. So now imagine three-dimensional means what? It is having 6 direction. If you consider one cube, so one cube that I have shown you about the reactivity. One cube is having 6 sides. So I think he brings the pen, so I will explain you by the pen. Now this is two-dimensional structures. So in two-dimensional structures, this part, okay, the front and back, this is available for reaction, But in case of nanocube, one side, another side, third side, fourth, fifth, and this front is 6. 6 side is available for reaction. 6 side is available for reaction. Remember sugar example. So if 6 side, 1, 2, 3, 4, 5, 6 side is available for reaction, so the performance will increase. Surface area is more. So it will give the higher performance. But if only 2 dimension, what will happen? For example, if you are giving energy to this 2-dimensional material, only electron on the surface of this 2 dimension will activate and try to emit, okay, only here. But here, if you give energy, the electron on each side, they will activate simultaneously and the performance will increase. So ideally, more area is available for nanocube than this one. So 4 years before, we have published one research paper that was on indium selenide. From 2-dimensional structure, we prepare nanocube, and that nanocube shows higher photocatalytic performance. This part I will show you in the green energy application, where you will understand why 3-dimensional structure is also equally important than 2-dimensional structures. So 3-dimensional structures, all X, Y, Z is possible to grow simultaneously. Now here X will grow, Y will go, and this Z will also grow. 3 direction it is grow. Sometimes this X and Y will grow fast and this Z might be slowly, but it will increase. So it will be 3-dimensional shape. Like this, okay? So all 3 direction is changing or modify. You can increase the length X, Y, Z direction and it can create 3-dimensional structures. So 3-dimensional structures, we can control their morphology, because when you prepare the nanostructures, you understand how much size it grows. At particular temperature, at particular voltage, current, energy, whatever technique you are using, you understand the parameter, you can control their growth. Whatever size you want, your desired size of nanoparticle, you can create of this 3-dimensional material, because growth mechanism is easy to understand if you are making the 3-dimensional structure. When I will explain that indium selenide nanocube, there you will understand how this 3-dimensional material can be useful to control their size, or easy to understand how to control the size. So this 3-dimensional nanostructure is very important because of their higher surface area, okay, and all sides are available for reaction, and that's why they can use for various purposes, catalytic or magnetic or electrode material. So it is having application in energy as well as in the environment field, or maybe magnetic application. And some of the material have porosity. Porosity means some material like zirconium oxide material, they have a particular pore, those we call porous material. If you put metal particle in that pore, their performance increase. Example are nanoballs, nanocoils, nanocones, nanopillar, nanoflowers. Here you can see the example, okay. It grows in all direction, okay. If it don't grows in all direction, then it will be plate-like or maybe rod or tube-like structure. But when it grows in 3 direction. So you can see such kind of formation of particle. This is another example, like low magnification, 3D, three-dimensional crystalline TiO2 nanostructure. So this is 3-dimensional. They are attached to each other. They are not separated, okay? 2-dimensional means they are separate layer or sheet. They are separated from each other, maybe layer or maybe sheet. This is another example. So this one is AG silver. So here X, Y, Z, this direction can be controlled, okay? So to understand 0, 1, 2, 3 dimension, how will you remember that this is 0 dimension, this is 1 dimension, this is 2 dimensional, this is 3 dimensional? Dot 1 dimension. Only x-axis increase, only x-axis increase 1 dimension. X and y-axis increase 2. X, Y, Z axis increase 3 dimension. So this way you can basically understand or remember how this nanoparticle is classified and why they called as a 1 dimension, 2 dimensional and 3 dimension. If you want to see the example, if you want to see the example of this 0 dimension, 1 dimension, 2 dimension, 3 dimension, carbon is a classic example, is a good example which exhibit a different allotrope. Now, carbon, simple carbon material like graphite, we called it as graphite, it is carbon, okay? What are the different allotrope of carbon you know? Graphite is 1. Other, say loudly. What are the different form of carbon? I cannot hear.
Diamond.
So graphite, diamond. Other? Any other? Any other? Allotrope means different form of same material but different form, like graphite C60. So we have graphite, we have diamond, we have C60. Other? Carbon nanotube, we got 4. Other? Any other? Charcoal? Yes. 5. Any other? I told you before. No? I think there are graphene. You might told I might not listen. Graphene. How about graphene? So graphene is also allotrope. Carbon has several allotrope. Okay, carbon is the most widely used material. Okay, which has various shape. Diamond, graphite, fluorine, carbon nanotube, graphene. These are allotrope of carbon. And carbon has special specification. I am not going. Initially, diamond is having a certain kind of atomic arrangement. So, if it is in diamond shape, it is hard material. You cannot break the diamond easily. Why? Because it has sp3 hybridization. The way carbon atoms are attached to each other, okay? So this arrangement, okay, one carbon atom, another here, this is 4, and down is 4. So this tetrahedral arrangement of carbon, we called it as a diamond. We cannot break it easily. But one of the slide I have shown you, and here also same thing, this is graphite, okay? So when you rub the pencil, this bond easily break and it convert into the sheet. Same material, but different crystal structure, atomic arrangement is different, property change. So that's why carbon is a special. So carbon nanotube, fluorine also different. How atom is attached to each other, you can see it make a ball, fluorine, okay? Sheet, then different property. So this bulk material, diamond bulk material, graphite bulk material, carbon nanotube, tube, okay, one dimension, two dimension, okay, two dimensional. So here you will find one dimension, two dimensional, three dimensional of single material that is made up of carbon only. But what is the difference? You can see the difference, how the carbon atom is attached to each other, and that decide their property. So if you are making a particular nano material, you can control them. You can control them if you understand how their basic structure is going to form. Once you understand how the growth is, whether growth is happening this way, or this way, or this way, then which parameter is important? That parameter you need to change, and it is possible to control the size of your nanoparticle. So these are, okay, the example, a unique example. There might be another, but as for my knowledge, I feel that carbon is the most volatile material that can be found in 3-dimensional, 2-dimensional, 1-dimensional, and 0-dimension. So how this formation happens? Graphite convert into graphene. You are doing by mechanical force. So how this 3-dimension, okay, this is connect to each other. I shown by dotted, I don't know, you are seeing it. 3-dimension means this single hexagonal carbon ring is attached to another carbon ring. That is 3-dimension. But if you break this connection, if you make it, then it become graphene, that is 2-dimensional material. But if this sheet, like paper, okay, paper, if this is sheet, if this sheet you just roll it and make like tube, then it become nanotube. And if you wrap in a such a way that it will make a football like structure. So this football like structure is nothing but 0-dimension. One element, 4 different allotrope. All allotrope is in different dimension. 0-dimension, 1-dimensional, 2-dimensional. So this process of rolling, wrapping, or breaking occurs from the bulk material, and bulk material can be converted into 2-dimensional, 1-dimensional, or 0-dimensional. So this way you can understand to control the size and growth of a nanostructures. So I think this will be the last slide for lecture number 2, and it is almost going to be 1 o'clock now. Let's have some question. If you have some question, we can go for question. Is there any question on classification of nanomaterials. Do you have any question? A particular type of material you want to research about their size, about their structures? Any question? Yes. Yes. If you do from big to small or small to big, okay? In the synthesis, I have lecture number 3 on synthesis. There I will teach you how we can make the nanomaterial. Whether we can go from bigger size to smaller size, or we can start from smaller and go for the bigger. Both way is possible. Okay, when you want to build one big structure, one big apartment building, you start with very small thing, you connect it and you make the big structure. And if you want to make a small structure from big, then you basically cut those parts, and if you are interested only one, then you cut everything, you remove, and you got the small part. So those kind of formation of nanoparticle is called as growth mechanism, and growth of nanoparticle is possible in two ways. We call top to down or down to up. There are two ways you can make this nanoparticle, nanomaterial, and that will the topic for, I think, class number, lecture number 3. Is there any other question? I hope. Yes. Yes. Now, when you are looking for the application, in your application, what is important? Less area is important, more area is important, conduction is important, semiconductor is important, band gas is important, light emission is important. That decide which material is better. So, yeah, so structure, because I have shown you effect of size and shape. Okay, structure means you are talking about. Yes, so each structure, let's say two-dimensional structure. Now, these two-dimensional structures is useful for various applications. Now, you will see people are doing research for photocatalysis or battery application, or they are working on two-dimensional. But you want to work on zero dimension. Which one you will choose, whether 0, 1 or 2? It all depends on their property. You have to study their property. Which property is useful? Okay, we cannot judge. First we make the material, but we never judge that this material, especially if you are making the material for the first time with different structure, it may be 1, 2, 0 dimension, nothing matter. But you must understand how it grows and what is the good property in that nanomaterial. If you understand this material exhibit a certain property, then you can decide application. It is very difficult, like you make two-dimensional or one-dimensional material and you go for certain application. Application is decided by properties. Like I'm working on photocatalysis. So for my application, I always look for the material which has high surface area. No matter it is two-dimensional, it is three-dimensional, or it is one-dimensional. It must have high surface area. If has high surface area, it can. Or other application, like I'm working on field electron emission. So there also, if you apply electricity, electron excite So that is electrical property. How these charges, you know, give the performance when you apply voltage or electric field to them. So that decide the application. If you make certain nanoparticle having one dimension, immediately it is very difficult to decide whether we can choose for particular application. If you do the research, like you read certain papers, and if you get certain idea that so and so material can be used for this type of application, my material is different, okay, you can go for that application. It may work. So both way, either you do the research on previous published paper, or you understand your nanoparticle and decide the application. So there are two ways you can deal with your nanoparticle. Any other question? Are you hungry? It's almost 1 o'clock. Okay, thank you very much. Thank you very much. So, thank you, thank you. I will see you tomorrow. Okay. So with this, I think they can go for the lunch, right? Yeah, okay. So please enjoy lunch. Yeah, please announce if you have anything. Do you have anything to announce? Yeah, please. Thank you for enlightening us in the area of nanomaterials. So we are
Vaira Distinguished Scientist of the Year in 2016, Fellow of the Award in Physical Sciences Fellow of the Luminescence Society of India in 2017, Academic Audit Member of VNIT Nagpur in 2017, and Transfer of Technology Award in 2018. He is a visiting scientist for a Nanodhera Gnostics USA, and Grassroots Innovators Virtual Mail Award in 2020, National Innovative Research Excellence Award in Physics in 2022, and is a world top 2% scientist in material sciences, and NIT Warangal's Research Excellence Award in 2024, among others. During the COVID-19 outbreak, he developed and patented a unique virus disinfect system called All-in-One Ozonit, which can kill all types of viruses within a few minutes without hazardous chemical or gases. This technology was well appreciated and awarded by the Ministry of Electronics and IT, and an Indian patent was recently granted. His postdoctoral experience at Nanocrystals Technology, New York, USA, and subsequent visits as a visiting scientist enriched his expertise in synthesizing and characterizing binary and ternary nanophosphorus for white LED applications. While at CSR NPL, he actively led the Alternative Energy Materials Group, aiming to develop novel nanophosphorus systems and devices for various strategic applications. He licensed a yellow-green emitting afterglow phosphor material to the Indian paint industry, Mrs. Cataline Infra Products Private Limited, Nagpur, for 11.50 lakhs in September 2016. He and his team transferred 2 more technologies to Defense Laboratory Jodhpur and 1 technology of AC-driven electroluminescent panels to ISRO. His other R&D interests include the synthesis and characterization of nanophase luminescent materials for LEDs and spectral energy conversion in silicon solar cells, fabrication of electroluminescent panels for backlighting of LCD panels, development of primary color emitting long persistent phosphorus for dark vision display applications, development of radio luminescent screens for high energy 80 MeV X-ray real-time imaging and biomedical applications of nanophosphorus. He has 14 years of teaching experience and 28 years of research experience, having supervised 10 PhDs, 2 MPhil and 25 MTech theses. He has 11 granted patents, 23 chapters in books, more than 247 research papers in SCI journals of repute, 25 virtual journal papers, more than 250 national and international conference papers, 3 general articles, and 2 technical reports to his credit. Many of his research papers were cited by Nature and appreciated by nanotechweb.org, verticalnews.com, IBM.com, etc. He is also an editorial board member for the International Journal of Luminescence and Applications and a reviewer for many international journals including RSC, APS, AIP, Wiley, IOP, Springer, and elsewhere sciences. His research credentials as reported by Google Scholars are H-index 45, item index 156, citations more than 7358. As a principal investigator, he has handled independent sponsored research projects worth more than 5 crores sponsored by SERP DST, DAE, BRNS, DRDO, CSIR, and MOE. With the support of other faculty members, he has instrumental in bringing the DST FIST program, FIST project worth rupees 2.75 crores to the Physics Department NIT Warangal for the procurement of XRD and FESM machines during 2020-2025. So with this brief introduction, I welcome Dr. Harna sir onto the dais, please, and give a big round of applause.
I would like to invite Sir Pankaj to present a memento to Professor Harna. Please, sir.
Good afternoon, everyone. Please excuse me for my sore throat anyway, but I'll try to be more precise. Thank you, Dr. Venkatesh, for calling me for this event. So anyway, you will be learning many preparation of nanomaterials by many methods. But today I would like to highlight on spectroscopic characterization of these nanomaterials. So once you make the nanomaterials, what are the things you are going to measure? Okay. And I suppose that nanomaterial, you have an introduction about the nanomaterials, and the best part or the very characteristic thing about the nanomaterials is the specific surface area. The surface to volume ratio increases tremendously when you go to smaller and smaller size. I think these things might have been told in the morning sessions. Okay, just for clarity I am just explaining you. So what does it mean that how does the surface area increases when you go to smaller and smaller dimensions? I'll take a small example. Take a glass of water and keep it for evaporation. At this type of temperatures, at room temperatures, it may take few months to evaporate the whole liquid. The same glass of water, if I put it on the floor and then make it, if I increase the surface area, what happens? Within minutes, it will dry. So what is the difference? The glass of water is same, the volume is same, but in both the cases, why the time is so important? Surface area means if you try to increase the surface area, there are a lot of applications that will come up. Okay, so earlier a glass of water, the only mouth of that one is responsible for the evaporation. Only that much area is responsible for evaporation. It takes months together. Okay, so not only this, not only the evaporation, reactivity, catalytic property, many other properties will enhance or decrease, or you can say there will be an alteration in the properties. Okay, so this is the basic things I would like to highlight, and you know that this is our institute, and here you can see our institute website, and then Department of Physics website, and my own profile. If you are not very well about writing this much things, you can just scan this QR code. It will take you to our website where you can see the activities of our department. So basically we formed a group in our department. We are about 16 faculty. So out of which we formed a group called Energy Materials and Devices, where I am one of the members, and Dr. Rakesh and Dr. Uday Kumar. So we three together work for energy devices, and Dr. Rakesh will be discussing about his activities in tomorrow's session, tomorrow, day after tomorrow's session. So luminescent materials and devices, this is my own area of research where I have 5 students, 4 SRFs and 1 JRF working with me on different applications of the fluorescence, phosphorescence and many other devices. Not only that, so some PG students also we encourage to do project works. For example, Daksha, she is from Metallurgy and Material Science Engineering. She has passed out this year, but she did a very good project with our section. So because of the interest in material science. And not only that, another student called Guru Prasad, he visited us. He is from NIT Srinagar. So in his vacation time, he visited us and worked in our department. So we encourage other PG engineering students also to work if they have interest. And apart from that, we have an integrated MSc program, which is BS MSc program. So in this, those students are also involved in research activity. Whenever they have free time, they will come and they interact with us. And out of this, the Purunjay has even published a research paper also in one of the ACS journal. So that's how we encourage our students also to participate and work along with the research scholars. So today I would like to highlight these things, but maybe tomorrow and day after tomorrow you will be acquainted with more production techniques. But today I would like to show one process called auto combustion process, which I have a patent on that. That is the process demonstration I am going to show you. What is the importance of that one I would like to tell in 1 or 2 slides. And then we will discuss about what is electromagnetic radiation, how different wavelengths are useful for the spectroscopic analysis of various materials, their applications, characterization, and these are UVs, DLS, Raman, IR, PL, TOFSIMS, EDAX, and EES, XPS, UPS. There are many other techniques. So we try to catch up on many of these techniques. So if you see the preparation of nanomaterials, there are 2 approaches. These are the basic approaches. One is called top-down approach and another one is bottom-up approach. Top-down, as the name suggests, that from a macroscopic material, if you mill it down to bring the size to smaller segments, then it is called top-down approach. There are various techniques like sputtering, etching, and ablation type of techniques, or mechanical or cryo type of milling at very low temperatures, or explosion type of process. There the bulk big material is scaled down to smaller sizes. Whereas there is another approach called bottom up approach, like from atoms or molecules you try to have an interaction between that will lead to a formation of smaller nuclear means particles, and they try to grow, and then finally we will end up having material in the nano regime. So nanomaterials, you can say they are intermediate, as you can see. You want to point on that? Or I have back this. I have this. Nanomaterials are something which are intermediate between bulk and atomic level. So they are somewhere in between. And you may see that there are many nanomaterials that have properties similar to that of individual atoms, and some may be exhibiting properties similar to that of bulk. So that depends on the range. Suppose they fall in the range, means higher side of nanomaterial size, which is similar to bulk, which is nearer to the bulk thing, it may act as a bulk-like particle. So if the particles are very small, like few nanometers, 1 or 2 nanometers, which are like few atoms composed at one place. So it may show similar properties that of individual atoms or molecules. But nevertheless, one thing you have to remember that these nanoparticles are having a size which is in the colloidal region. In chemistry, you can call it in the colloidal region, where the gravitational forces will not be acting upon. Even there is no, if you have the gravity, still they are not being settling. For example, you have a glass of milk. Milk is having particles in the colloidal region. So if you keep a glass of milk for for more time, do you see that all the white thing is settled at the bottom? No. Even if you dilute it, it doesn't happen, because those are not being attracted by the gravitational pull. So that is the another characteristic of this nanomaterial. So out of these, there are many other bottom-up approaches, like vapor deposition, sol gel process, spray pyrolysis, chemical evaporation, electrochemical deposition, auto combustion, and bioreduction. There are few processes I have highlighted. The list is not ending here or there. So we will be highlighting a process called auto combustion. Let me introduce that process and a small video how it works, and then we'll go to the characterization techniques. Because in the afternoon, evening, I'm going to show the demonstration of the same experiment, and you may feel that without introduction, if I show, then you may be feeling bored about that. So auto combustion process, you know the combustion. Combustion is a process, burning of something in presence of oxygen, isn't it? So when you, how you can have a burning of certain material, it should be like a combustible liquid. It should be like fuel. So some fuel type of thing is there, then you can have ignition to that. Okay. So imagine a car, a small engine, where a motorcycle or a scooty engine. You have a carburetor where the fuel will come into that, as well as there will be an air filter. Air filter is the one where from air is sucked, and it will be a combination of oxygen and then fuel will be there. Proportion will be, uniform proportion is maintained in that carburetor. So when there is a ignition due to spark plug, so it gives maximum momentum. If there is a disturbance in that one, suppose you have given choke, that means you have freely allowing the petrol to get into that very freely. You don't have that much thrust to that one. You don't have, it won't run properly, your vehicle. Similarly, if there is a blockage and air is not properly circulated, then also you will have the same problem. Then you will obviously go to the mechanic. Then he will adjust both the things with a fine tuning, and he will say now it will work and it will give you maximum mileage. That's the thing. So here also we should you should give oxygen to a combustible fluid where your nanoparticles should be there. So what is the advantage of this process? You can make monodispersed standalone particles in at least in few grams. Usually any nanoparticle preparation technique you take, classical techniques, so all precipitation type of chemical reactions and others, where you see you will end up having maybe micrograms or milligrams of nanomaterial. If somebody asks to give 1 kg or not 1 kg, even 100 grams of nanomaterial, that fellow will be fainted, because that much to make, he has to spend few years to deliver that. But without having bulk quantities of nanomaterial, you cannot achieve any practical application. You cannot go for any application. At least few grams or even kgs you have to make it. So that's the big challenge, and nowadays few techniques have come up. And that's the reason why in 2023 all the three Bruce, Bavendi, Bruce, and Ekimov. These are the three scientists. They got the Nobel Prize. Bruce and Ekimov, they are responsible for the making of quantum dots. Discovery of quantum dots. Whereas Bavendi is responsible for the production of nanoparticles in larger quantity. Only for production technique he got it. So Nobel Prize for 2023 in chemistry. So I will show you this process. It is the advantages is it's a one-step process, and you can make any oxide material very easily, standalone particles. Okay, you can control the temperature and you can control the size, and only thing is it will burn like a flame with few seconds, and you can see that all the contents in that one, they go out as nitrogen, carbon dioxide or water vapor and so on. So initially we started with a furnace, tubular furnace with a quartz tube and keeping that fuel. So how to make the fuel I'll tell you. Fuel containing the nanoparticles. Okay, once it is burned, we'll get one side like it's a one-way valve type of thing. You can imagine like a pressure cooker type of thing. Something you are cooking inside. If the pressure is excess, it will come out, but nothing goes in back to it. And then the amount of atmosphere that is present inside the container, that is with respect to the amount you are putting in. The combination should be proper. Then only you will have a combustion inside. So later on we moved to a vertical furnace from 3 sides heating. This is what our fuel is there, and it burns inside, and there is a exhaust which will pull away all that nitrogen and carbon dioxide and so on. Later on we have optimized such that even on a hot plate you can do it. No need to have furnace, vertical or horizontal furnace and everything. You can just put it on a simple heater or a hot plate. Okay, so that much we optimize. So what is the thing we have done? For example, here you can see, you can take any metal nitrate. Okay, metal nitrate. Here I have taken strontium nitrate and aluminum nitrate. Okay, nitrates can be dissolved in water easily. I want to make strontium aluminate. That was the condition. So strontium nitrate, aluminum nitrate. Okay, and this is urea. Urea and these nitrates and urea, they form a combustible liquid like petrol. The proper combination of urea and nitrates. Nitrates are oxidizers, and this is a reducer. So it's called redox mixture. Redox mixture is highly combustible in nature. So this, when you put it, this proper combination of this one, when you put it in a furnace or on a hot plate, it burns. Initially it boils, and excess of water, nitrate, whatever it is there, it will go away. It forms a jelly type of thing, and suddenly it catches fire inside a beaker. You can see the flame. And the flame temperature is adiabatic flame temperature we have calculated. In a beaker it comes around 1261 Kelvin. That means it's around 1000 degrees centigrade. No glass beaker will sustain, because glass beaker will melt at 625 degrees centigrade. But a quartz beaker you can use, it can sustain little more, but it is for few seconds. So a beaker also will sustain. If it is for longer time, beaker will break, because it cannot sustain that temperature. So we'll see today, if we are lucky, then beaker will be saved, otherwise we have to forgo the beaker. But this is the adiabatic temperature we have calculated, and this results like this. Like from this is the top view of the like a flame it comes, okay, and then when the flame is generated inside a beaker for a few seconds, immediately after that it will cool down, and you can collect all these nanoparticles which are very, very fine. You can just with a glass rod you can collect few grams of this thing. Okay, and since I have added a fluorescent dye as a dopant into that, so I could see the color. When I shine ultraviolet light, I can able to see the color emission. That means uniform doping has been done. So how properly we have developed that. So that indicates that. So this is what we are going to see, and we have patented also on this type of process. Process patent has been done. So here you can see that I have taken nitrates, metal nitrates, and then urea as the combination. Both urea is very economical product. Okay, very easily you can get it. You can have, instead of urea, you can have glycine, you can have alcohol, you can any combustible thing you can just put it, but high purity it should be there. So urea will dissolve in water. Nitrates also they dissolve in water, so you can just mix and make a slurry of that. Okay, so when I just put it on a preheated, means already heated hot plate, I have just put it. You can just watch it here. So and I have put a lid here just to, because urea sublimation temperature is 130 degrees centigrade and water boils at 100 degrees centigrade. So while boiling, along with the water vapor, some urea also may go out. So to restrict that one, I have put a small cover, a petri dish cover. So initially you see there are fumes that are coming out. They are related to the water vapor. So after that, brown fumes starts coming up. So they are nitrates, excess nitrates that are coming out. So after that, suddenly it forms a thick slurry, and carefully you observe there will be a very beautiful flame that comes out for a few seconds. Now nitrate fumes are coming out, very brown, dark brown fumes. Now see, there is a sudden catch of fire inside the beaker. That's it. Experiment is done. So for few seconds, the high temperature flame. So what is the advantages of having that flame inside? So if you have that flame, then the particles that are there in that combustible liquid, they will be like, they will have surface bonds, dangling bonds. So when these within the flame, they are all satisfied, means all these dangling bonds can be removed. You can have the particles, sintered particles, highly crystalline particles. Okay, so most of the sol gel technique or any other technique, if you adopt, you will get amorphous type of materials. But here you will get crystalline material. In a beaker you can make the crystalline product. So that's the thing. Maybe my students will demonstrate in the afternoon, maybe zinc oxide or some other nanomaterial they will show you. Okay, that's the thing which I wanted to demonstrate in the afternoon. So let us come back to our talk. So you know that light is electromagnetic radiation. So electromagnetic radiation consists of different parts. Okay, and you know that electromagnetic radiation means we have both electric and magnetic vectors. They are perpendicular to each other. Okay, they try to propagate in that direction. And if you see the electromagnetic spectrum, continuous spectrum, from shorter wavelength to longer wavelength, so it can be divided into gamma rays, X-rays, visible region, infrared, far infrared, microwave and radio waves. So out of this, we have this visible region is a very small region. Okay, and then ultraviolet is also responsible. So most of the characterization techniques will be dealt in these directions. For example, gamma rays can be used for certain characterization. See, if the particle, if the distance between the lattice points is very small, usually the lattice, this thing you see in angstroms, few fraction of angstrom between atom A and atom B. So in order to probe the structure, you need to have a wavelength similar to that one. So that's why X-rays are having very less wavelength. So those things are responsible if you want to probe the structure of that one. So similarly, infrared, microwave and so on. So if you take this part and then analyze, you have ultraviolet spectrum and then visible spectrum. This is the visible spectrum. And again, ultraviolet is divided into UVA, B, C. UVA is responsible for from 320 to 400 nanometers, and 280 to 320 is ultraviolet B and ultraviolet C. Luckily, this ultraviolet C we are not getting from the sun because it is being blocked by the ozone layer that is present, which is harsh UV, you can say. But in laboratory, we can generate it, or we can have lamps for that. UVA and UVB are available in the sun's light. Okay, and UV, of course, we need to expose ourselves to the sunlight daily. It is good for us. And if you are continuously exposing for longer time, you see The aging effects also will be there. UVA is more prominently, if you are exposed to that one, you will be aged fast. And UVB is responsible for the burning sensation. Whenever you go into hot sun, you see that there is some pinching or burning effect, that is due to UVB. And there is some action spectrums also that are available. So one of my research scholar is working on making different wavelengths suitable for phototherapy, photodynamic therapy. When suppose if you want to cure any skin disease, that skin disease has an action spectrum. If you match up, if you make a lamp source which is having similar to that of that one, then without any medicine you can just shine that light and you can cure that type of skin disease. So that action spectrum and our wavelength should match. For example, you might have seen like when a newborn baby is there, again he will be put in some light and they will put it, that's called infant jaundice. They get jaundice and they put it under ultraviolet light. Those ultraviolet light, they charge a lot, these doctors, but that's a very broad wavelength, broad source they will put it. They don't put a single wavelength. That's why even the baby is very fair when he was born, and when he is continuously exposed to that UV radiation, the complexion will decrease a bit. That is because of ultraviolet radiation. So we can tune these wavelengths to particular disease, so that directly you can put that wavelength and you can try to remove that without any medical treatment. So that's called photodynamical therapy. So that's the thing, that's the action spectrum. And this action spectrum for human beings, you see from this to this region, this is responsible for the generation of vitamin D in our body. Okay, so vitamin D, we say in the early morning you have to go for a walk and then you should expose yourself to the sun. That is, our body also has some biological, I don't remember the formula, that some PPIX it is called. So that chemical will be disintegrated into vitamin D. Similar compound exists in trees, plants, where it will, the exposure of sunlight will cause chlorophyll, development of chlorophyll in plants. So similar things, so that's why the action spectrum of PPX it is shown. So every wavelength has particular importance in characterizing the materials. So here I have listed on a few spectroscopy techniques, for example gamma rays emission in this region. Okay, when you want to probe the materials of very small dimensions or inside the material, what is being happening. So similarly X-ray absorption or emission, fluorescence, vacuum ultraviolet. Vacuum ultraviolet is less than 200 nanometers. In the earlier slide, here below 200 nanometers, it is called vacuum ultraviolet region. So vacuum ultraviolet spectroscopy, ultraviolet and visible absorption, UV-vis, you call it as UV absorption, infrared FTIR type of absorption, microwave absorption, EPR, NMR. So these are various techniques that are available where you can probe the material and understand. So these are the type of things you can get it. The nuclear dynamics or inner electrons, bonding between the material and all these things you can prove. So these are energy units for electromagnetic waves. Usually we represent energy in electron volt. Okay, and sometimes they may show it as per centimeter or hertz. Okay, so or micrometer and so on. But usually we go with EV, electron volt is the one which we use it. Okay, this characterization of materials means we are going to analyze the structure and properties. So if we are going to study the structure and properties, then we can call the characterization. And characterization techniques, usually there are two types, microscopic and spectroscopic. So microscopy and spectroscopy, these are the two basic things where you can analyze the material completely. Actually, I thought of having complete this thing, but it is exceeding more than 2 hours, so I just limited to the spectroscopic thing only this time. Microscopy means all your SEM, TEM, HRTM and so on, those things will come up. So here I have listed out few things. Microscopy is the characterization where you are probing and mapping the surface or subsurfaces. So the optical microscope, SEM, TEM, FIM, STM, X-ray tomography and atomic force microscope, these are all the various techniques where you can analyze this material, that you can do it. And spectroscopic techniques are those where you will try to analyze the chemical composition and the variation in the composition or the crystal structure. So all these things. So today we are going to highlight or discuss about these techniques only. So EDAX, energy dispersive X-ray spectroscopy, wavelength dispersive X-ray spectroscopy, X-ray diffraction, mass spectroscopy, secondary and mass spectroscopy, and EELS, electron energy loss spectroscopy, and so on. The list is also not ending here. There are many things. Few of the things which we will discuss today. See, the applications of these spectroscopic techniques, you can see, you can find out whether the composition which you made has some impurities associated to that. You can find out the structure of the organic compounds if it is organic, but I'll be limiting my talk to mostly to the inorganic. Okay, I'm not that much familiar with organic things. And quantitative analysis, you can estimate the quantity, and qualitative analysis, sometimes you can simply say that yes, this is present, but we cannot estimate the number. Chemical kinetics, functional groups, and analysis of some pharmaceutical drugs, molecular weight determination, HPLC detection, band gap calculation. So many applications, many things you can do with this. For example, if you take the characterization, nanomaterial characterization using spectroscopy techniques, there are two types of spectroscopic techniques. One is imaging technique and the other is spectroscopic method. Imaging technique means you can just see a picture of that. For example, SCM, TEM, AFM, whatever you see is you get a similar type of photograph type of thing, and then you try to analyze that. Okay. And then spectroscopic methods are those where UVs, dynamic light scattering, Raman, infrared, PL. So all there, you don't get any photograph. There you get the spectroscopic distribution. From this you will analyze, isn't it? So basically these are the two ways with which we can able to estimate the materials. And the another interesting thing about the nanoparticle is, depending upon the size of the nanoparticle, same, material is same, depending upon the size of the nanoparticle, the color of the solution changes. For example, you see these quantum dots. These quantum dots are made up of cadmium selenide, zinc sulfide core and cadmium selenide shell. These core shell structures you see all are having the same composition except the size. The bluer one is the smaller size and the bigger one is having the cluster of nanoparticles is bigger in size. So only with the size you can able to estimate. Okay. So here you can observe that few atoms to number of atoms. So when the size is more, then you will get more towards this. This is not the body color, it is the photoluminescence, means you shine ultraviolet light and you will be able to see the distinction. Otherwise all may look as a transparent liquids only. Okay, that's the indication. So always remember that the smaller particles always will have a blue shift, bluer side. So it gives just by, this is the qualitative behavior. Initially, what just by looking at that one, you can say, okay, it is towards blue means particles are very small, towards red it is bigger, like that you can estimate. And then with the graph, you can quantitatively measure. And you can see that how it is distributed. If it is towards blue region, it is blue shift, and this is for red shift, and so on. So UV visible spectroscopy, usually it runs from 200 nanometers to typically 900, 800 or 900 nanometers. That's the usually they do it. So there is a near UV region like 200 to 400 and far UV region below 200. So this is ultraviolet spectroscopy. If you want to study exclusively, then it should be done under vacuum conditions only. Ultraviolet spectroscopy or vacuum ultraviolet spectroscopy, which is below 200 nanometers. So essentially that needs vacuum, either vacuum or in an inert atmosphere. Otherwise, the vacuum ultraviolet, when it is generated, which is below 200 nanometers, it will be absorbed in the air itself. Before reaching the sample, it will be absorbed by the air molecules. So it should be under, strictly under vacuum conditions only you can able to observe. And usually this will nowadays very rarely people are using that vacuum ultraviolet spectroscopy, because earlier we used to have plasma TVs, plasma televisions, where the fluorescent materials are used, where the vacuum ultraviolet light is generated, and that will hit that sample, and that will try to give the emission. But as the LED TVs have come into picture, LED displays, the vacuum ultraviolet generated plasma TVs have faded up. So hardly people are using that vacuum ultraviolet. But if you, even if you want to study about that, that is available in University of Allahabad, UP. So ultraviolet absorption spectra arises from the transition of electron within a molecule from lower level to higher level, and you can calculate the energy relation, that is. So the total energy that is associated will be equivalent to the electronic transitions plus vibrational transitions plus rotational transition, because any molecule you see, there will be electronic transition, rotational and vibrational movement. So all the energies, when you add it up, that gives the total energy, and the energies of electronic will be much higher compared to vibrational or rotational. This is the sequence it follows. So always remember that in any semiconductor or any other material, the electronic transitions are always vertical in nature. Whether it is a direct band gap material or indirect band gap material, always the electronic transitions are vertical in nature, because the nuclear position of the atoms is constant, it will be stable. So don't imagine that if they, actually the difference between direct band gap, indirect band gap is, if the valence and conduction band are lying exactly one above the other, it is a direct band gap. And if it is slightly, the conduction band is little away from the valence band, so it is called indirect band gap. So you can see here, even though the conduction band, of course here this is called coordination model. Here I am not showing a band type of thing. There's a classical way of showing is here valence band and conduction band as straight lines, bands. But quantum mechanically you have to show it as like this, potential wells. So always you can expect a transition which is direct, vertical. You cannot have a cross type of thing, because it is nearby, so we will take a path like this. No, electron will never take a slanted path. It will always go straight. That's why exciting indirect band gap material is difficult compared to direct band gap. So most of the semiconducting devices or whatever you take, they are direct band gap materials only, because excitation is easy. You give little energy, it will go to the higher energy state. So that's called the Frank-Condon principle. So what are the electronic transitions? Because we came to know that apart from rotational, vibrational and electronic is taking much greater part. So what are the electronic transitions that are possible for us? So it is pi star, sigma star, n sigma star. So all these 6 are the possible electronic transitions, out of which these 2 are forbidden transitions. There is no material which has this one, and this type of transitions never exist in any material. For example, if you see here, so there are different materials with various transitions, but these 2, pi to sigma star, or from this sigma to pi star, these 2 transitions are forbidden transitions. Okay, so double bond, triple bonds comes under n pi star transitions. Aromatic compounds have this type of transition. Oxygen, nitrogen, sulfur has this type of transition. CH bond is having sigma star type of transitions, and so on. But no compound will have this type of transitions. Okay, I'm not going to very detail about this transition. We have to talk about many other effects, and this is about the shifts and effects, like blue shift. If a material shows blue shift, then the size is very small. It shows red shift, the size of the particles are very bigger in size. Similarly, if there is a peak is more distribution, if you see instead of more Gaussian, you have a peak like this, then chromatic shift, or you can say the color purity of that material you can assign. If you have a broader thing, means more colors are involved in that. If you have a narrow band, means very limited colors that are existing. So hyperchromic, you can call it as hyperchromic shift. And UVs, you will follow this Beer's law, isn't it? So Beer's law is nothing but the absorption versus the concentration. So initially, when the absorbance takes a linear path with respect to the concentration, whatever concentration you put, and you put it in a small vial and then put it in that UV spectrometer, and you see what is the absorbance of that, and it will be constant for a while, and after that it will be, the saturation will takes place. And these UV spectrometers of different sizes that are available in the market, for example, UV Spectrovis Plus is a very tiny instrument, and which is affordable also. Within 1 to 2 lakhs only you can get it. And here is a small space where you can insert the cuvette, okay, and measure the UV spectroscope. And there will be a lamp. What is there inside is a lamp, and there is a small slit, and there is a dispersion device. Dispersion device could be a grating or a small prism which can be oriented. So you can have again a slit, which is what you can call a wavelength selector, because all wavelengths will be falling there. Which wavelength you want exactly? So this will be moving, so that the same whatever wavelength you require, that will fall on the sample, and that will go to the detector. But most of the times we use another system. If it is a bigger system, then we will use a reference cell. Always we go with a reference cell of a blank sample with respect to your sample, then you will find out. Otherwise, in this case, what happens is, whether that is given by the solvent or your material, we don't know. It's a combination of that thing which is detected here. So if you want, then what you have to do, you have to put a blank. First record the spectrum, take the data. Again put a sample with the nanoparticles. Again take the spectrum. Again overlap. Remove you have to do certain calculations to arrive at the absorption of the particles only. So here in this case, you will have a reference cell. Directly you can nullify the effects of the solvent, and directly you can go. Usually they use alcohol or hexane or water. So these three will be used as a reference cell to remove that. Okay, and you can have if it is only ultraviolet spectroscopy, you will have ultraviolet lamp. Otherwise UV vis it is there, then ultraviolet lamp and a visible lamp. So after the ultraviolet lamp, immediately that will shut off, and then visible lamp will glow on. So the spectrum for a whole UV to visible will be carried out. So dynamic light scattering is another interesting spectroscopic technique where you can find out the particle sizes as well as of course the smaller particles will have more dynamics related to that. There is a system called zeta sizer. So zeta sizer is the one which tells you about the size of the particles as well as the charge that is present on the particles. Okay, so that is based on the principle of DLS. So you can see the bigger particles have slow movement and with a particular laser, usually not a red laser, they use only for dynamic light scattering they use red laser, otherwise a green laser 532 nanometers will be used. So smaller particles have more scattering and you can see lot of distribution that you can get it with that, and different sizes of the particles you can estimate. But this size when you compare with that of a SEM or TEM picture, you will see a different thing, because here the instrument doesn't know whether it is a single particle or a combination, like a agglomerated particle. It doesn't know. It simply measures the diameter and then simply it will say that 50 nanometers. You may think that I have done particles, I have seen the SEM, it is about 10 nanometers, here it is saying 50 to 100 nanometers, how come it is? So if the particles are charged, obviously when they are moving dynamically, they try to collide and they form agglomerates. So agglomerated size may be the thing which this is estimating. So usually what they put is, they put a small stirrer bar at the bottom, so continuously that will be rotating so that the particles never settle. They will be floating around and a laser light will be there. So with this one they will try to detect the size, effective size of the particles, whether it is a agglomerated or bigger particles. Okay. So this is a DLS instrument, very small tiny instruments nowadays they are available. So you can see with respect to time also, if there is any reaction going on or the size of the particles are growing. Suppose you have taken high concentrated liquids and you have added, you see that slowly it is growing. So if you want to see the dynamics of that, how it is growing, 1 minute, 3 minutes, 7 minutes, every time you can see the distribution. Okay. So another interesting technique is Raman spectroscopy. So Raman spectroscopy will give you about the inelastic scattering that is taking place and which typically uses 532 nanometers. And then you can see that the inelastic scattering mediated by the electronic polarizability of the medium. So both the polarization and inelastic scattering both are responsible for this, and a material or molecule scatters irradiant light from a source, and most of the scattered light is at the same wavelength as that of the laser source. So if usually that doesn't happen, if the same wavelength is being scattered, it's called Rayleigh scattering. So Rayleigh scattering again it depends on the size of the particle and the wavelength with which we are doing that. Okay, and size is inversely proportional to 1 upon lambda to the power 4. So that's the Rayleigh scatter size. Okay, so that's how the wavelength and the size are linked there. But Raman scattering is the one where it's an inelastic scattering and different wavelengths will be produced. You shine one wavelength and you'll get a altered wavelengths. Okay, so if it is not the same wavelength, then it is Raman scattering, and that is very weak also. It is very difficult to identify these Raman lines. So Raman lines could be like this is the initial wavelength which you are shining at the particles. You may get anti-Stokes and Stokes. So what is the difference between Stokes and anti-Stokes? Stokes lines means always when you are giving a higher energy, you are getting lower energy signals, like you are giving ultraviolet, which is higher energy, and you are getting some photoluminescence in the visible region. So UV is higher and visible region or IR is a lower energy region. You are giving higher and getting lower, that is Stokes shift. Anti-Stokes shift means you are giving lower energy and you are getting a higher energy. How come it is possible? It is like a photon is absorbed, and by the time it is de-excited, another photon will come. It's like stepping. So 2-3 photons, and then the final emission is from the top to bottom. Okay, so that is called inelastic. I mean, that is called, you can call it as upconversion. Okay, upconversion process. Usually you are giving a more energy. Okay, the electron goes to the higher energy and then come back to the yes. So Raman scattering in crystalline solids, okay, you have different selection rules. Energy conservation has to be maintained, momentum conservation has to be maintained. Okay, selection rules should be determined for the crystal symmetry. All the crystal symmetry also one has to take care. Okay, I'm just skipping all this. There are various for various materials you can find out the LO, TO type of modes. Okay, so there are various things you can calculate and you can just go through that. And infrared spectroscopy is also another technique. If you use Fourier transform infrared spectroscopy, so this spectroscopy technique is very much useful for determination of bonds, stretching, bending, and all types of bonds you can estimate within a molecule. And you can see this is the instrumentation where infrared spectroscope source, and then you will have a sample and a reference, and again it will be determined. So usually you have different signatures for different bonds. For example, nitrogen and hydrogen bond, which lies somewhere here, 3600 or so. OH bonds have a particular signature. CH bonds, triplets. So all this, they have a signature things. Okay, at a particular temperature, so they show this type of vibrations at this stage, and these vibrations are very much useful for determination. Like for example, we have the Indian Standard Time. Okay, every country has their own standard times. So how do you say that that standard time and my whatever watch I am wearing, my time and that time, how it is varying? So how do you ascertain the time? So the atomic clocks, actually they use cesium and some other atoms. They use it, they immobilize it with lasers, or you supercool it, and when you start increasing the temperature, for every particular degree there is a particular frequency with which the atom vibrates about its own axis. So that is called frequency. With frequency is number of cycles per second. With that one they estimate the second, accuracy of the second. From that one the accuracy of time will come into picture. So Indian Standard Time we are maintaining at National Physical Laboratory, my earlier employer, where we used to have that, still we are having another new system also, with cesium atoms are being immobilized, and then we check for the vibrations with which it works. Why the time is so important? So time is very much important for not for trivial things like my watch and your watch. If it is differed by 1 minute, doesn't matter for us, isn't it? But time matters when it is for a longer distances. If you are space travel or something, if you are doing, and if you want to estimate the distance, then the fraction of second it matters. Okay, distance is equal to speed into time. So if the time there is a fraction, then your calculation of distance, everything, speed you are anyway monitoring. The distance will be difficult. The instruments say that you have reached, but you have not reached that position. So in thousands of kilometers, then few hundreds of kilometers, there will be a difference in that. So in NPL, National Physical Laboratory in India, who is maintaining the Indian Standard Time, so they are maintaining up to 26th decimal point of a second, 26th accuracy of, after dot, 26th place. So that much accuracy is required, and that is the time which is given to the ISRO to launch their satellites. ISRO doesn't believe on somebody else atomic clock. Atomic clocks are maintained by many countries. They don't believe on other countries. Obviously, if they try to give a small variation in the time, our all space shuttles will be destroyed. It will never reach the destination. So we have to maintain our own thing. We should not believe others. Okay? And even if you want to convert, I mean, you have a laptop and at the right side corner you have the time, na? Just click it. It will show the world time, and then it will show Windows time. You can change it to Indian Standard Time. It is www.nplindia.org, time.nplindia.org. If you do. Okay, just put it up. So you can tune down to our own time. See that still it is 1 minute is there, but how come these fellows are maintaining different time like that? You will be unnecessary, you are scolding IRCTC, but IRCTC is not doing that. Your time is wrong. So if you maintain this time even for your laptops and desktops, So you will be synchronizing always with Indian Standard Time. Okay, and you see, just for observation, whatever time which is there in your Microsoft thing, just before switching to this and then refresh it, just see the time difference. You will see that there will be 1 or 2 minutes difference would be there. So if you try to take Windows timing and start doing your space experiments, everything will spoil. Okay, so never believe. You should believe on yourselves only. Okay, so this is what. Usually for infrared spectroscopy, formaldehyde is taken into consideration as a standard sample. So it has many bonds that you can just take it as a reference things. For example, CH2, symmetric stretch and asymmetric stretch, scissors type of, and CO stretch, CH2 rock, CH2 egg. So all these types of things are mostly existing in many other things, and that's why it is taken as a reference material for FTIR. And if you just want to compare FTIR, because both are giving the different types of bonds only. So here you can see FTIR is more sensitive to functional groups, especially OH stretch, which is available in water, good for studying constituents of organic molecules. Here Raman is more sensitive to C double bond O and C triple bond O only. So you can distinguish between diamond and amorphous carbon or graphite. So if you want to distinguish the difference, because it's always between carbon things, so Raman spectroscopy is used. And studying backbone vibrations of the organic chains, so there it is useful. Here it needs some sample preparation is required, because for FTIR you use KBR and then you make a pellet and other things. There it is not required, so little bit of sample preparation is required. So here you can study the little bit of fluorescence light also. If it is giving a different wavelength, you have shined one wavelength and you are getting different wavelength, that also you can able to see, but here no such emissions will come out. And it is having good sensitivity, good microscopic technique also, whereas here it is very difficult to observe these Raman lines, so you can say fairer sensitivity, and it's also one of the good microscopic techniques. So let us have a small break for tea, and after that we will resume. Okay. So luminescence is a cold emission. What you can say, it is a cold emission. There's nothing heat is involved when it is radiating. Like if you try to heat a metal to very high temperatures, okay, you see that there is an emission from that, light emission. But that is associated with the heat you are providing. That's called thermionic emission. And there the red hot of iron, or and then still if you increase the heat, you will get white emission also, different emission colors, but that is proportional to the temperature you are giving. That you cannot call it as luminescence. But if it is a cold emission, it could be based on the reactions, or it could be like you are shining one wavelength and you are getting back another wavelength. So where there is no heat is involved. So non-thermal type of emission from an object, and preferably in the visible region, it's called luminescence. But nowadays the segment has increased, like ultraviolet luminescence, infrared luminescence also people are calling. So you can extend little bit, but in all the way it should be non-thermal type of emission. You should get it. Okay. So there are different types of emissions, like if it is you are shining optical radiation and you are getting the optical light output depending upon the excitation. Like I am exciting with photon, then it is called photoluminescence. If I am giving electric charge or electric field I am giving, and I am getting the light. That is called electroluminescence. For example, your mobile phones. So you are providing energy through batteries and you are having a display. So that is electroluminescence. So there also material is being coated from inside. So that is DC electroluminescence. Similarly, LEDs also come under electroluminescence. You are providing electricity as excitation source and you are getting light output. And if you are giving cathode rays or the electrons, okay, then it is called cathodoluminescence. Like earlier CRT, cathode ray tube and other things, you have electron gun and a fluorescent screen. So the different energy of the photon electrons will strike and you will see. That's why old TVs, when there is a power off, it will put up into a small dot, and if you try to touch that one, you will get shock because everything is concentrated, and that small dot, still it disappears, it contains lot of charges. So that is called cathodoluminescence. Radioluminescence means if you apply the higher energy radiations like X-rays, okay, you can call it X-ray luminescence or radioluminescence also. And chemiluminescence, if you see, you know the exothermic and endothermic reactions, like you are mixing two liquids, if the test tube is getting heated up, then you call it as exothermic reaction. And if the test tube is cold, then you feel it is endothermic reaction, like it is absorbing heat from outside. Why can't only heat? Why can't light? Suppose if I mix two chemicals and get a light coming out of that one, it is possible. So that is called chemiluminescence. Okay, and there are some bioluminescence also, some biological bacteria. You can see in WhatsApp videos like some of the seashores in the night, blue algae is lot of luminescence, it is there. And these what do you call that? Firefly, in Hindi it is called jugnu. Telugulo minuguru purugu antaru. I don't know how many people are from outside this state. You know the firefly? You see in the fields, in the night time you see some of the insects, glowworms. They are, and in some of the movies also nowadays they are showing this. So that is bioluminescence. Actually it secretes some organic chemical, like we get sweat, and that organic thing which is called luciferin, that's the secretion from that glowworm. So it secretes. But where is the excitation force? The temperature of the body temperature of the insect is taken as the excitation. So that's why you see then it glows and slowly it diminishes, because when it is losing the heat, so it will glow, and when it flies again it generates heat. So that is provided to that one, and again it will glow and it will come down like that. So it is very highly fluorescent, that luciferin. So similarly, that's called bioluminescence. So depending upon the source of excitation, you have number of names. You can triboluminescence, you give pressure and then you see some glow, that's called triboluminescence. Most of the crystals you will see, and even you see some of the marble stones, when you try to strike it, okay, you see specks sparking, okay, that's pressure. Due to pressure you will get that one. So wherever you get light using various phenomena, then you can call it as that type of luminescence. Okay, so the only difference between this fluorescence and phosphorescence is if it is instantaneous emission, like you are shining something and immediately you are getting different wavelength, that's called fluorescence. Phosphorescence is the delayed fluorescence, like it is absorbing and it is delivering in the evening times, like night glow stickers, radium stickers and other things what you see. So it is absorbing, and then the absorbed radiation only it is emitting in the dark times. So that is called phosphorescent. So essentially how to make these materials is, you can dope an activator which is responsible for the color. So crystal is the one which absorbs the radiation and then it transfers the energy to that particular activator which glows. So you can have various numbers, various types of emissions, like band edge emission. If electron is falling from conduction band to valence band, it's called band edge emission. From activator trap level to the activator level, trap to the valence band. So these are various possible mechanisms one you can have in this, okay. And depending upon the color of emission, there is a CIE colorimetric diagram where you can locate it and identify, because there are various shades of color. You see, we don't know the difference between yellowish green and greenish yellow. What is the difference? People write it as greenish yellow and somebody is writing yellowish green or green yellow, yellow green. All look same but has a different meaning. Like if you see this colorimetric diagram, which is approved by all over the world. So here is bluish green, blue green, green. This region is called green, yellowish green, greenish yellow. So a slight change in the color will have a different thing. But we don't know the difference, so that simply we will write it as this color, that color. So, but when you want to publish a paper or you want to transfer a technology, if you write this loose language, nobody will appreciate that. You should use a common language or a code language, okay. So here you have x-axis and y-axis. So if you say that I have prepared a material which is having green emission with these codes, x this much, y, xy coordinates this much. So where it lies, so that indicates to that person, okay, you are talking about this color which is located in this one. Even when you go for painting of your house, that fellow will show you a shade card and all numbers will be shown. You show this one, that depending upon that number, he brings that paint to you. So same thing here also. So this is how internationally it is approved. We use many colors which are not existing in international literature. For example, the color which this girl is wearing, you say cream color. There is nothing like cream color or beige color, okay, or apple green and all. These are our Indian language, okay. We use many words like that, okay. So, but they are not internationally acceptable. So we have to use something which is everybody can understand that, okay. So to have this type of photoluminescence, if you take a metal piece or metal thin film, and then if you want to go for a photoluminescence study, it is not advisable, because photoluminescence arises because of two reasons. One is defect or a dopant. Either it should have a defect or a dopant, okay. Defect can exist if you have a semiconducting material, okay, and if you have an insulator, then only you can have defects or dopants. If you dope certain element, it will form an activator level. Somewhere between the valence band and conduction band, somewhere it will form an either acceptor or donor level. In metal, it is not possible, isn't it? So metal, if somebody brings a metal and go for a photoluminescence test, it should not be done. Only thing is you can do if it has an oxide layer, which is pure metal you have taken, but there is an oxide layer formed on that one. Oxide can be detected, but not a pure metal. Okay, so either you should have a semiconductor or a insulator, because it can be detected only defects or dopant. So photoluminescence in semiconductors, you know that we can make many devices and we can run through that one. Photoluminescence spectrum at different temperatures is also nowadays very important. Usually we do room temperature photoluminescence to find out the defects and dopants, but if you do low temperature studies, then you can estimate the density of that defects. Suppose you made a single crystal, very good crystal with almost minimum defects, but you want to know that what is the number, or if it is minimal defects means how many number and what type of defects, the point defect or a Schottky defect, Frankel defect, what type of defect. For that one you have to go for low temperature studies. You have to go lower and lower, like up to liquid nitrogen or liquid helium temperatures. Then you can quantify about the peak. See, at 220 Kelvin also some broad spectrum is observed. So you can, this is at when you go to lower and lower temperatures like 6 Kelvin, you see there are certain strong peaks have come up. So the area under the curve of these things you can calculate, and you can estimate the density of those defects, density and number also. So those things you can determine using low temperature photoluminescence. So this is the setup, consists of low temperature cryogenic cell will be there, your sample holder, and there is the whole thing will be immersed in liquid nitrogen. So the sample as well as the holder, everything will be at low temperature. Then it is like when you decrease the temperature, the motion of electron, everything will be freezed. Everything will be freeze. So they'll put it, and while exciting the material, they cool down the system. So all the electrons that have went to the conduction band, they will be freezed there only. So then they switch it off all the excitation sources, and only in the dark conditions there will be detector, and slowly they start increasing the temperature. You can put a heater and do it, or simply open that valve so that liquid nitrogen escapes out, and slowly from minus 78 degrees centigrade, 78 Kelvin, it will start coming to the room temperature. When it starts coming to that one, slowly that's increasing of temperature. Then when they start vibrating, and slowly the photons that are absorbed and they are present in the higher energy state, they try to come down. So at particular temperature, with that one we can, how many photons have come up with the detector, whenever it shows some glow curve, it is called some glow curve, area under the curve and other things you can estimate, and you can find out what type of defects that are present. So that's the calculation part one can do. So this is the cryostat in this. So impurity levels, as I told, either you dopant is in little quantity, if you dope it is called dopant. 2% or less than 2% if you dope in any material, it's called dopant. If you put 5%, 10%, then it's called impurity. We actually, research scholars, they use very loosely about this dopant or impurity. Sometimes they write dopant, and sometimes the same paper they write it as impurity. The difference is, if it is less quantity, less than 2%, you have to write it as dopant. If it is more than that, 10, 15% like that, then it's called impurity. And if you write 50% dopant, it is wrong. 50% impurity is also wrong. 50% you are adding means you are alloying it. It's a basic, it becomes one of the component of the system. Okay? So like that one has to use it. So you can estimate the shallow impurity levels or impurities that are present in the system. This is a simple example. You see zinc sulfide. Zinc sulfide is having a band gap of 3.6 electron volt. But if I try to dope with a copper ion, so it's quantum dots of zinc sulfide. If I dope with copper ion, I can get green emission. But same zinc sulfide, if you try to dope it with silver ions, then I can get blue emission. Same zinc sulfide, if I dope it with manganese, I'll get orange red at 590 nanometers. So the interesting thing is, in photoluminescence, like if you have a high band gap material or insulating material or a wide band gap semiconductor, it is good, because same material we can create many number of colors. If you have silicon, what is this? Silicon is also semiconductor. Silicon, germanium 0.7 electron volt. Okay, here it is 3.6 electron volt, and silicon it is 1.1 electron volt. So what is the colors you can bring it? You cannot bring, because 1.1 is so small. Even if you dope something, 1.1 itself we cannot see. Okay, so it should be 2.4 or 2 electron volt, then only our eye can able to see. Okay, so in that one, 1.1 electron volt itself is so small, and whatever you dope it, like p-type doping, n-type doping, whatever you do in silicon, so we cannot, visually we cannot see whether it is being doped or not. Okay, so if you want to see photoluminescence, you should have wide band gap semiconductor, at least 3.5, 3.6 electron volt gap or more 6 electron volt like insulator, then you can play with various dopants. You dope this one, you will get one color. You dope with some other element, you will get different color, and so on. Okay, that is for the doping. And if you don't dope anything, you create defects, then also you will get distribution, and then also you will get color. In both the ways you can detect. Okay, see the excitons that using the photoluminescence excitation spectrum, you can able to detect what are the excitation wavelength that is responsible for it. Okay, if time permits, we'll show once again those things. Exciton is nothing but the electron hole pair, conjugated pair, which moves around in a semiconductor. So usually we use the term called quantum confinement. In most of the nano studies, you try to listen this word. Is it not quantum confinement? What is quantum confinement? Anybody? You see, whatever peculiar property you see in the research paper, you write it, it is maybe due to quantum confinement. We don't know what is quantum confinement, but we will try to write it as all these effects may be due to quantum confinement. See, quantum confinement means if the exciton Bohr radius you can calculate for a bulk material. Suppose you have a bulk crystal like zinc sulfide only. So zinc sulfide is having a band gap of 3.6 electron volt, and exciton Bohr radius, using this formula you can calculate quantum mechanically. You can calculate the band gap as well as you can calculate the exciton Bohr radius, EBR it is called. Here it is not mentioned, maybe here. Exciton Bohr radius you can calculate with the rest mass of the hole and electron, and when you just substitute here, you will get the exciton Bohr radius for any particular material. The exciton Bohr radius for zinc sulfide is about 2 electron volts. No, not electron volts. 2 nanometers is the exciton Bohr radius. Suppose if I make a material lesser than that one, if I make zinc sulfide lesser than exciton Bohr radius, then I can able to see the quantum confined effects in that one. How is it possible? Like imagine like exciton Bohr radius of any bulk material is a standard one. So 2 electron volts, 2 nanometers I told, means the distance between a hole and an electron is 2 nanometers. Suppose I made zinc sulfide lesser than 2 nanometers, like 1 nanometer particle I have made, quantum dots I have made. That means this thing is squeezed and is put in that one. It should exist in the material. It cannot be out of that. Exciton Bohr, you have that exciton should be present in that one. Means the size is this much, but your particle is this much. But still that particle should have this. So the exciton is confined and is present in that. So that is called quantum confinement. Got it or not? You can calculate exciton Bohr radius for any material. Suppose 10 nanometers, suppose a compound material you are working, the exciton Bohr radius is 10 nanometers. If you make the same compound lesser than 10 nanometers, then essentially what you see, that exciton Bohr radius is squeezed and is present inside that. That's why it will show some abnormal properties. So there could be 3 types of thing. One is strong confinement. Like you have the exciton Bohr radius this much, you have particle very small. So this much is to be squeezed and present in that small size. So it shows very strong confinement. So very abnormal properties in quantum dots you see is because of strong confinement. Second one is weak confinement. Suppose your exciton Bohr radius is this much size, like let us say 5 nanometers, and your particle size is also 5 nanometers, 5 to 6 nanometers, near to that one. So it is easily fitting into that with a little confinement. So that is called weak confinement. Okay. So strong, medium, you can say medium confinement. Weak confinement is the one, suppose your size is this much and your particle is this much. So easily it can be there inside with less confinement effects, or weak or poor, you can say. So depending upon the size of the particle what you are making, but any preparation method you adopt and try to make the nanomaterial, try to calculate the exciton Bohr radius. And if the exciton Bohr radius, once you calculate, or you can check in the web also, in the internet, what is the exciton Bohr radius of this particular compound, and to find out that, then you estimate the size, then you can compare. Then only, after comparison only, you can able to know whether it is strong confinement or weak confinement. If you want to understand more about this one of my papers is there, confinement effects in zinc oxide nanomaterial. I put it here. No, I have not shown it here. In nanotechnology, long back in 2008 or so, it was published in the journal IOP Nanotechnology. Confinement effects in ZNO quantum dots. That's the title of the paper. Okay. In that one, strong, medium, and weak confinements of zinc oxide particles have been very clearly established. Okay, there you can find out. So see, you can see the absorption shift, like smaller particles to the bigger particles in diameter. This is using photoluminescence only, you can able to estimate this. This is about the emission, PL emission, and depending upon different sizes you can able to see the same. This is all zinc oxide material only. I have done extensive work on that. On the, you see the precipitated powders also, they are quite strong photoluminescent in nature, and we have got lot of appreciation for this, because usually when you type in Google saying that quantum dots, you'll see cadmium selenide and cadmium sulfide, different colors you will see. You don't see zinc oxide. We are the first in tuning the colors in zinc oxide depending upon the sizes. So for that one we got many appreciations for that, international appreciation. So fluorescence spectrometer, you have many things like light source and a monochromator where the grating or prism will be there, which will select one wavelength which will fall on the sample cell, and that will be measured. Okay. So there is a thing called, sometimes you can use gratings also instead of prism. Gratings also you can have and measure it. And there is another thing called time resolved emission spectroscopy. Time resolved in emission spectroscopy is one where you can find out the rest time of electrons in the trapped state. Suppose it has excited to the conduction band and it has come back to some level, some dopant or something, that level before it coming back to the valence band. How much time it is residing in the excited state? We know that in conduction band 10 power minus 8 seconds is the standard one. Every electron will go and 10 power minus 8 seconds it will come back to the ground state. But trapped states are either shallow traps or deeper traps. So various traps can be tuned. So the resting time of an electron in the trap state will vary. So if you want to estimate that one, then time resolved spectroscopy technique is the one where you can do it at room temperature and low temperatures also. And with that one you can calculate the quantum efficiency and fluorescence lifetime also you can. So these things you can do, and the luminescence spectroscopy is a very interesting and widely used technique where you can do spectral measurements like excitation, emission spectrum and so on, and you can measure the lifetime. That is called the lifetime of time resolved spectroscopy or lifetime measurement, where fluorescence lifetime, phosphorescence lifetime you can measure, and polarization measurements also you can do, and some miscellaneous like quenchometry and other things for organic those who are working in organic molecules, they can work. So many things can be done with fluorescence spectroscopy. Okay. There is another system called TOF-SIMS, time of flight secondary ion mass spectroscopy, and this is another interesting case where, and laser SNMS, secondary neutron mass spectroscopy. So these are little sophisticated techniques where you can able to estimate or quantify the elements that are present in that one. So every vibration has a particular frequency, and they can estimate the composition. Suppose you made some material and you want to estimate. Okay. So with these graphs, it is difficult to say that there are many compounds that are even organic, like binding also. If you have put a small organic binder to make a pellet, and that also comes out as a signal, then how to estimate that one? So there is a in the same there is a system called correlation analysis. Suppose you assign maroon color to manganese and zinc some blue color, and the overall sample is looking like this. It's a mixed color. If it is showing a mixed color, that means the distribution or the dopant, manganese is the dopant. So manganese has been dissolved, or completely, very uniformly it is being dissolved. So if you take a manganese versus zinc spectrum, it shows like this. So this is with laser top sims only you can able to do that one. So not only the elemental measurement, but also mapping. You can see, I am unable to understand with the graphs. Let me show pictorially. So immediately it will show like this. So it's if it is at 45 degrees angle, then that means that the doping is very, very uniform. I'll show another example where the uniformity is not proper. For example, this. So this is a strontium aluminum oxide doped with europium. Europium and dysprosium also. Two dopants are there. So strontium blue color is given, europium dysprosium is green color, and aluminum as red color. So you see the combination here, it is not proper. See, somewhere only blue it is seen. That means only strontium oxide is present. Somewhere this green is there. That means europium is somewhere lying here. And somewhat red portions are there somewhere. That means only aluminum oxide is present. That means whether you, while making the sample or grinding or preparation of that sample, it was not uniform. So it shows the distribution. And you show the aluminum versus strontium, it is not following the 45 degrees angle, very scattered. And similarly aluminum versus dysprosium, because both are 3+ ions. So the dopant dysprosium in aluminum also, it is not following. Means with this spectrum or the graphs profiles, you can simply say that sample is not a good sample. Of course, the elemental, simply no need to have a uniform mixture. Even if you mix it little bit and give for that laser SNMS or top sims, you will get the composition. But really it is doped or not, how will you know? Only with these profiles only you will be able to know that. Okay, this is the long back we have published this paper in 2005. So in nanotechnology, laser top sims and laser SNMS investigations of dopant distribution in nanomaterials, nanophosphors. Okay, this also you can. Let us stop it here. Few more techniques are there anyway. I'll come back to you after some time. It's already time is up. So we'll move to the physics department. One of my research scholars will take you there. Okay. So their demonstration, which I have shown the very first slides. So zinc oxide, probably I think they are planning for zinc oxide. They will tell you. So here I did not mention you how to make the redox mixture. I simply said nitrates are oxidizers and urea is reducer. Okay. Suppose you want to make certain compound, how to make it. So that explanation they will provide you. You can ask questions and you can make a note about those things. Okay. And one of the simple thing they will demonstrate. They will mix it in front of you, and that slurry with a beaker, they will put it on a furnace. Okay. And then you can, if you want, you can take video also, and you can watch how exactly it happens. It's an explosive type of reaction. Don't be very near to that. As I told, if the the flame lasts for longer time, little more time, there could be an explosion of glass beaker. So if somebody hurt, I am not responsible. So little make a U type of thing near that chamber so that everybody can see. Okay, and my scholars, they will take precaution in doing that, and they will demonstrate you the making of nanomaterial. Before that, they will take you to my laboratory where we have made many fluorescent materials. I work on fluorescent materials. So they will show some display box, and then on the board already it is written how to make this zinc oxide nanomaterials using auto combustion process. Similar process you can adopt for your thing. The calculation, it's a very simple calculation. They will tell you. You should just know the valency, like carbon 4 plus, hydrogen 1 plus, oxygen -2. So these valency, if you know of your compound, you can make any. Basically, for oxides, not for sulfides or any other oxides, easily whatever oxide you want to make it in nano form, you can make it. So that's the beauty of that experiment. And if you have any doubts, you can always write to me or discuss with me. Okay. Thank you very much for your patient listening, and I'll be happy if you have questions, 1 or 2 questions. No questions, then we can. Yes, sure. Okay. See, as I told, it's a explosive type of reaction. All nitrates are explosive. Okay? Even when you talk about bombs which are dropped, okay, Hiroshima, Nagasaki and all, so they all contains this TNT, trinitrotoluene, nitrogen compounds. Okay, all nitrogen compounds are oxidizers and they are very dangerous. Nitrates, what we use in the laboratory, we are using in very little quantity, so they are not that much dangerous. So what you can do is, suppose you want to see, the auto combustion process is very good for oxides because we are giving oxygen to particular system. So oxides, any oxide, whatever you name it, whether it is a binary oxide or a ternary or a quaternary or multiple oxides also, you can make it. That is first thing. And only thing is, suppose I have a zinc oxide bulk material, bulk powder, micron powder, but I want nano of that one, let us say. So take that zinc oxide and dissolve it in nitric acid. You will have zinc nitrate. That zinc nitrate, you add urea, will become a slurry, I mean the transparent liquid. That you put it on furnace and you will have zinc oxide with nano form. How it is, why it is nano, and how much nano, or what is the shape and structure, you have to go with XRD and some other SEM and other things. Morphology, usually you will get spherical morphology, but you know zinc oxide can exist in many forms. But here in zinc oxide, mostly because the surface energy of a spherical particle is minimum. So it will try to have a minimum entropy. So all particles will be spherical, near spherical in nature. Okay. So if you want different structures, you can play with the fuel. See, instead of, as I told, instead of urea, you can use alcohol. Alcohol is also combustible. Glycine, citric acid, tartaric acid. So these are very easily available chemicals. Okay, yes, different morphology. And there are 2 types of combustion. What is flame combustion, flameless combustion. So in both the cases, see, if you give proper atmosphere, you will have flame. That's called flame combustion. If the ratio is not proper, then also you will have combustion. Like instead of carbon dioxide, carbon monoxide will come out. Okay, but combustion will take place. that combustion product, flameless combustion also, like if you use glycine, you never get flame. But suddenly it will kick out the lid which you have put it, and you see this tiny particles floating around, and some are there in your beaker. So if you try to see that one, you will get finest particles, like in few nanometers you will get it with glycine, but you never get flame. Okay, so depending upon the redox mixture, the type of mixture, like see, you have kerosene also, you have petrol, you have diesel, okay, you have alcohol. Whether all will burn with similar thing? No. So similarly here, if you change the fuel, you will change different shapes, morphology will change. But for urea, what I have seen is more or less it is spherical, where you can get little flame, and you will be amazed to see that in a beaker can you make the nanomaterial with a small stove or a hot plate. So that is the idea of showing you this. Okay, any other doubt in this? You can play with the pH also, pH of the solution. Okay, the starting temperature, like heater, if you are putting on a hot plate, it will be around 300 degrees centigrade or 350 degrees centigrade, isn't it? Suppose you put on a furnace at 800 degrees centigrade, like preheated furnace. Take the solution, put it directly inside. See, why I am asking you to put it on a preheated furnace, preheated beaker, to avoid the evaporation of urea what you are adding. So if you put it inside and start switching on your furnace or this thing, slowly it will start boiling. By the time it reaches high temperature where it should ignite, by the time half of the water and urea also will go out. So for here also, while the explanation, they will tell you, we are adding stoichiometrically, whatever is amount of urea is required, we are adding double. Why we are adding double? Because with some of the thing is lost, even though we are putting a lid, some of the urea is lost. By the time after the losing also, when it forms a jelly type of thing, so then it contains similar required composition. Suppose you don't want to put anything extra, what you have to do? Because take this nitrate and put little water. You don't know exactly how much water you need to put. Okay, you put little 1 ml or so, and then you have added urea. Urea also for dissolving you are putting water. So excess water you are putting. So what you have to do is you take that clear solution, put it in an oven for overnight without lid, maybe 60 degrees centigrade. So in the night, overnight if you put it, all excess water will evaporate and it forms a gel. Then you can put that one on the heater or furnace, you will have your nanomaterial done. But if you want to do now, we cannot have that much time, na? So if you make it and if I ask you to come tomorrow, half of the people will not come. So in order to save our time, we are adding excess urea and let it boil here itself and let it go little bit. But by the time it jellifies, and you will have enough urea and nitrate mixture, which is highly combustible, and it catches fire in a beaker. Okay, so first you observe that practically, you see that, and then you can post on that questions to my research scholars also. They have done enough experiments on that. Still, if you are not satisfied, my email is there. I'll just put it on the very first slide. You can write to me that harnath@nitw.ac.in. I'll respond to that. Okay? Right. Thank you for your kind attention.
Thank you, sir. Thank you for your time and the excellent topic. So I request all the participants now, go to the physics department and see the lab, right? Thank you.